So the bus comes late and then I don't know what to do. Sorry. Okay. The last time I started with the introduction to Markov decision process, which are key to understanding stochastic games, especially from the point of view of algorithmic side. So what happened was that a policy in a Markov decision process that depends just on the day and the state of that day, and which are pure stationary in the sense at each state, a Markov decision process admits a pure stationary optimal strategy provided the action space is finite, the states are finite, and transition is Markovian. So I started with an example with the Markov decision process with just two states. And this, I want to recall the notation that in state one, there is only one single player who is interested in playing this game, and he receives $5 or whatever it is, and then remains in the same state with 60% chance, and with 40% chance he moves to the second state. If he chooses the second action, he loses $4, but he remains in the state one with chance 10%, and with chance 90%, it moves to the second state. That is the Markovian transition. And in state two, you have three actions, and those numbers explain what it is. And if I choose the last action, I remain in the same state. Okay. And then one can evaluate the expected immediate reward on each day when you start the game, the process in a state S on day one, etc. And those are the computations. So the more important theorem there is for each starting state S star, given any behavioral strategy, we have a Markov strategy which can essentially cover the same thing, same probability distribution on the state and action spaces. And there are three key theorems which are essential for computing the better policies. So if phi star is any Markov policy and a player adopts on day one only some new policy, new strategy, and then switch over to the original policy from day two onwards, and if that cannot be better than the original policy, then the original policy must be optimal. If it is true for every arbitrary f, then only. Suppose there is some policy where you adopt f on day one and use the policy pi, whatever was the pi, and if you can improve it at some state, then you throw the policy out and replace it by f. So you use a pure stationary policy f then onwards. And the third important theorem is for any discounted Markov decision process, the optimal value function in terms of the discounted value is a rational function in beta, where beta is a discount factor. And there exists some beta naught beyond which you can keep the same policy. And then you have two types of ways of computing the improvement of the policy. First thing is to start with, if you are starting with state S, and look for some f such that if you take any action A, you get on the day one, you get RSA. From then onwards, with the discount factor, you move to new state. And then when you use the policy F, then if this one is better than the current policy at some state, then the set GSF is non-empty. And then what you do is you replace the original policy by this new policy. As an example, I took the following simple example, which I did last time. So this is actually the policy improvement algorithm. Okay. Then I came to, given a bounded sequence, you consider what is called the Cicero payoff. It is defined by the limit of the averages. And then I talked about, in the case of a stochastic matrix P, the transition matrix or whatever it is, this limit always exists, and that limit is called the Cicero limit. And it has an interesting property that it commutes with the original matrix, and then it is idempotent. The next important theorem, which connects the discounted with the Cicero payoff, is by this famous theorem of Blackwell, which is given any stochastic matrix with Cicero limit Q, I minus P plus Q is non-singular. I minus P plus Q inverse is the limit as beta to the T, P minus Q power T, as limit beta goes to 1. And that inverse minus Q is this fixed matrix. That is this limit T equals 0 to infinity, beta to the T, P power T minus Q is this fixed matrix I minus P plus Q inverse minus Q. Now, how is the discounted payoff connected with Cicero payoff? Start with any pure stationary policy F. Start with any pure stationary. When you say pure stationary policy, it is something like F infinity. That means I would use F all the time, nothing else. Whenever I am in this state, I use the same F. That means if it is pure in that state, I use the same action. Then the discounted value is connected to the Cicero value by this equation. B beta F is phi F over 1 minus beta plus D of RF plus E beta F RF. D is this matrix. This I minus P plus Q inverse minus Q is D. So this is a fixed matrix which is called the deviation matrix. And this E beta F RF, when beta goes to 1, this will go to 0. The last thing goes to 0. So then I talked about this theorem of Zygmunt, that the two extreme ends cover the two interior ends. These are in terms of Abel sum, related to Abel sum. Not exactly, you have to multiply by something. Related to Abel sum. If these two extreme things collapse, the interior things also collapse to the same number. Okay, if they push you, and if you are caught in between those two, then they coincide. The remarkable theorem of Hardy and Littlewood, if the bounded sequence is Abel summable, then it is that means if the two limits on the thing inside coincide, then the outside also will coincide. Normally it is very strange kind of thing. And then there are two kinds of optimality. One is uniform optimal strategy. That means I use the same strategy for all beta sufficiently close to 1. The other one is nearly optimal. That means it approaches what this uniform optimal strategy approaches as beta goes to 1. They are close to each other. In fact, the other observation was that the policy-induced operator is monotonic and further a contraction. That helps you to convert our original problem. There are two ways of solving them. One is by policy improvement. The other one is by linear programming. So it is the linear programming for which the operator T, which helps because it is a contraction. And this is our reduction of the linear programming problem. It's what you do is it works. You could have taken summation US or summation some gamma S US, where all gamma S are positive. You could have chosen any positive number. Okay. And it is only by the dual we come to the answer to the question. It's not from the primal, it's from the dual we get the answer. So changing this to a stochastic game is essentially you have not just one player, two players, a row player and a column player. And what happens is in a stochastic game, you have finite number of states, finite number of actions for the two players, and then the immediate reward is something like a matrix game. It is a matrix game. And you have the same, instead of the Markovian transition, you have the same Markovian transition, but which depends on the actions of the two players. And that makes it more difficult to solve. So we could write every discounted payoff stochastic game as a value and as optimal stationary strategies. And then I gave the simple, an intuitive example, intuitive approach to what Shapley thought. All you do is, God says, I will help you to play from tomorrow onwards, but I want you to play for today. Whatever you can do, whatever the best thing which you think of the two players, you can play for just day one. And then from next day onwards, I will take care of the whole game. So the first day's payoff is RSIJ. And then future payoff with discounting gives you beta times PT Sij Vt with the value Vs. And as I started with a simple example where we noticed the payoff matrices, if you are given like this one, so intelligent way of playing this game is the same as playing intelligently this game. First day plus the discounted stuff. And what happens is these solutions become irrational. If originally you started everything with rational numbers, and certainly solution becomes irrational, but in a more complicated case, it can be a hopeless kind of function. Okay? And that is the reason why we may have to restrict ourselves, if we want to solve a stochastic game, to only subclasses. So what are some subclasses which one can think of? Here is the first one example that we discussed some subclasses earlier, but later I had a student. Okay. By name Syed, and then we were trying to solve a very simple stochastic game. That means in each state, only one player controls he has actions. The other player is purely a dummy. Okay? So suppose the state 1, it may have, say, 3 actions, and the player can choose these 3 actions with his own mixed probability. There you may have to use a mixed strategy. Stationary, but mixed. And then he keeps the same strategy whenever he comes there. But what will happen if it go? You see, some actions may push you to another state, or some actions may keep you in an excellent state, but from there you may degenerate. So you really do not know how to move around. Okay? So because you can make a lot on day one, but then you are pushed into the other person's state. It is the other person who is controlling, and he wants to minimize your income because it is a zero-sum kind, minimize. So it goes back and forth. So what can you say? That's the question. And the very interesting thing there is a pair F star G star. Suppose God came and told you that the value of the game is Vs. Now, I find a pair of strategies. If I used a pair of strategies, I get Vs. Are they optimal? That was the question. The one thing is to achieve the same expectation, but not necessarily they may be optimal. Even in an ordinary matrix game, you may have a pair of strategies which achieves the value. You take a simple example. You take a matrix with 2 rows and 3 columns. Imagine you choose a matrix with 2 rows and 3 columns. First row gives 1, 1, 3. 1, 1, 2, 3. The second row gives 3, 2, 1. The first row gives 1, 2, 3. The second row gives 3, 2, 1. So for player 1, he can choose the 2 rows with equal chance. So he can get half of 1 and 3 if he chooses the first column. If he chooses the second column, you will still get 2. If he chooses the third column, you will still get 2 with the average. Whereas player 2 can always choose the middle column and guaranteed a loss of only 2. But player 1 cannot choose only the first row and hope to get an average to it. It won't be an optimal. Even for a matrix game, it is not an optimal strategy, whereas for a stochastic game, it is true. That is the key observation. So the way it is done is you start with a pair of pure stationary strategies, F0 and G0, and try to lexicographically find an improvement. That means player 2 says, for example, I am going to use the strategy G alpha. Then player 1 finds the best F alpha plus 1 in terms of the Markov decision process induced by G alpha. Okay, once you fix one player strategy, it becomes purely a Markov decision process. Therefore, in that process, the best strategy against player 2's strategy can be found. Now, having found, he cannot improve any further. He says, I'm not able to improve any further. What should I do? Now, give me the chance. So now player 1 fixes himself to that strategy. Now player 2 is trying to pull down. And this is the process which goes back and forth. At some stage, neither one will be able to change. Then you stop, and that is your optimal pair. Okay. Here is a simple example. You have player 1. Okay. This game has 5 states. In state 1, player 1 has 3 actions, and he gets either 5 or 4 or 3 as immediate reward, depending on his action. Okay? Player 1 alone has possible actions. Player 2 is a dummy in that state. And then the chance that it remains in the same state is, if player 2 chooses the first column, it is the chance of remaining in the same state or moving to state 2, 3, 4, 5 is given by this probability vector. So that means if you choose action 1, the game jumps to 5th state. If you choose action 2, the game moves to state 3 with 20% chance and 5 with 80% chance, like that. And in state 2, these are again for player 1. If he moves to state 2, then he can choose first action and get 6 and move to state 5, blah, etc. And state 3, it is for player 2. That means he's losing, even though it's not an immediate reward, that means it's a loss for him. Okay. And R2, etc. So in state 5, it is a single action only. That means it is nature. So when you reach that state, with different probabilities, the system moves to various states. So you start with this strategy, F0 G0 equals, say, 1, 1. The first and first. Then he finds if player 2 is saying, I'm going to stick to G0. Now player 1 finds, instead of 1, 1, 3, 1 is a better strategy. And then he is not able to improve any further. He says, I'm not able to improve any further when you stick to 1, 1. So I'm going to be sticking to 3, 1. Then player 2 says, okay, if that is the case, I will jump to 2, 1. Okay. Oh, I'm not able to improve any further. Then it comes back to player 1. And he says, instead of 3, 1, I will jump to 1, 1 again against your 2, 1. You are right now at 2, 1. I am going to jump from 3, 1 to 1, 1. The original 1, 1, 1, 1 is different from this 3, 1, 2, 1. From 1, 1, 2, 1, you move to 1, 1, 2, 2. That means player 2 is improving more and more against that 1, 1. Namely, he reaches this state, 1, 1, 3, 2. And then the last one is 1, 1, 3, 1. So these are the actual computations, okay, when you calculate that. And what happens is, it is going, when you look at these numbers, let's look at that, phi beta F0 G0, whatever it is. The next one, in each coordinate, okay, for player 1, it is the same. And 3, 1, you see, 1, 1, 3, 1. Here there is an improvement. The first one is an improvement. And then here, again 3, 1, 2, 1, which means, let us see, there somewhere it is an improvement for the other player. He is pulling down. One is pulling up and another is pulling down. Okay, it goes on. And in the 6th round, it stabilizes. The proof depends on what I mentioned. If a pair of pure stationary strategies have as their expectation the value of the stochastic game, then those strategies are optimal for the stochastic game. This is not true, as I mentioned, for ordinary matrix games or for Cicero payoff stochastic games of perfect information. It's not true also for that. In Cicero payoff, you can construct a very simple counterexample. Okay. So what we were noticing was, even though we can use induction on the number of actions to prove the theorem, we never fully utilized the algorithm in a more efficient fashion, even though empirically we found there was an overall improvement for one player happening. And a new trick was needed, and it is achieved through what is called Patience theorem. So what is Patience theorem? I can simply explain by a simple analogy. You have a father and daughter. Daughter is the maximizer. The daughter wants to maximize the discounted payoff. The father wants to minimize it. The daughter says, I have one rule, Dad. You first tell me what strategy you are going to use. It is still a perfect information game. You tell me what strategy you are going to use. Then against that, you have to wait till I get the very best against that. Now it is the same as the first stage. Then after having done that one, the daughter says, I'm not able to improve any further, but you are allowed only one more move. I give you a chance to play only once. If you can improve in first round, you tell me. Suppose he finds something which is slightly better than what it was previously for him. Then as soon as it is done, he tells his daughter, yes, I have found this improvement. Then the girl says, now you have to stick to it. You cannot improve any further. You are not allowed to. I have to find the best against that. So this goes on, and this must terminate ultimately. Okay? So it is the father who is willing to wait patiently, allowing daughter to make the best against these small improvements. And what does Patience theorem say? Suppose F0 G0 is a strategy pair and G1 is a strategy for player 2 for a game with a fixed discount factor beta, such that against G0, F0 is not able to improve any further for this particular discount factor. Now, the girl says, the girl is sticking to F0, Dad, choose some strategy which is better than what you have right now. And then you have chosen only once. And the theorem is that the V beta of this discounted game, where father sticks to G0 and the best against that is better than the best against G1. That means for some betas, I can find such that for beta closer and closer to 1 kind, I can do this one. And this is what is called policy improvement for perfect information. It's not only for perfect information games, but also for additive reward, additive transition. The additive reward means RSA1A2 is R1SA1 plus R2SA2. It splits into two parts, separate parts. Transition also splits into two separate parts. So it is in this paper which extends with Matt Burke. Okay. The thing is, a policy improvement type algorithm will also solve perfect information stochastic games with average payoffs. And then this is the Blackwell sense, etc. There is something called the Blackwell optimality. A single policy is required to be optimal simultaneously across a whole range of discount factors. That is the uniform optimal policy. There is another that is uniform. There is another which is one optimal policy. I can give I see. I didn't put the slide for that one. Unfortunately, I took a picture, but I don't know how to project it here. Okay. So even though those things were done, I'm going back to how we started. Okay. This was this class, which is the single controller stochastic game. You start with this matrix. Suppose you have two states. State 1, the payoff matrix is 1, 2, 5, 0, blah, blah. State 2 is 0, 3, 6, 6, 2, 0. So the game wobbles between the two matrices. Okay? It's called a single controller stochastic game if something like this. Suppose player 2 is the only person who is controlling the transition, not both players. Only player 2. When he chooses the first column, no matter which action is chosen by player 1, the game remains in state 1. If you choose the second column, the game goes to state 2. So it is decided entirely by player 2. So if the transition is entirely controlled by one player, then you have a very unique advantage. Let us see what the advantage is. Okay. So if in A1, if you play intelligently, according to Shapley, it should be V1. So the dummy game which you create is, you play for day 1. For both players, he is asking. Then from day 2 onwards, God takes care of the thing. So even though God takes care of the thing, is interestingly, along the column, it is 1 plus b, 5, beta v1, 5 plus beta v1, 0 plus beta v1. Similarly, for the second column, the structure of this is, normally it will be a nonlinear structure, but here it is a linear structure. So each matrix game becomes a parameterized game depending on V. So if I want to compute an optimal stationary strategy for player 1, it can be found among optimal solutions of the linear programming problem, where player 1 tries to maximize the sum of the two states' payoffs. Subject to these constraints, okay, and okay, so x1, x2, x3 are the probabilities of selecting more than the probabilities, just non-negative vectors, such that x1 plus x2 plus x3 is 1 non-negative, blah, right? And similarly, xi1, xi2 non-negative. Okay. So if I take this example, simple example, I can find that both players have this strategy. Player 2 has a uniform optimal strategy. Player 1 has also, so that means in both states, he is choosing the two columns with equal chance. Whereas for player 1, let's look at that. Player 1 strategy must depend on the discount factor. Whereas for player 2, it is uniform optimal strategy. So in fact, F01 is 7 plus beta over 8, blah, blah. So player 1 also has a unique, in this case, optimal strategy depending on beta. But in general, it need not be unique. There can be multiple strategies. Player 2 is uniform. Player 1 adapts continuously with beta. That's what happens. And you can solve this problem by linear programming. Solving efficiently for the uniform optimal strategy for player 2 is still unresolved. Okay. Now, the critical use of Cicero limit for stationary policies is by checking these two conditions. This is the Abel inequality, and this is the Cicero thing. But the Cicero thing is dominating the general pi, average pi. The uniform optimal strategy of the Markov decision process is optimal for the MDP in the Cicero payoff also. In theory, we can find in finite arithmetic steps the Cicero optimal value for the MDP via the evaluation of Cicero payoff for various pure stationary strategies. Again, we can start with a single controller game. We can write down the optimal strategy inequalities, and you notice these things. So if you consider a beta discounted single controller stochastic game where the controller is player 2, then the game admits a uniform optimal strategy mainly for player 2 for all beta greater than some beta not close to 1. And the value is a rational vector function of beta for all beta greater than beta naught. So the Vries, Hordak, and Kahlenberg first result is to consider a player 2 control stochastic game with Cicero average payoff, an optimal solution F5U of the following linear program yields the undiscounted value of pi and an optimal stationary F for player 1. So it is to maximize the average sum over all states such that delta Ts is the Dirac delta function, minus Q is the transition here, and phi is the average payoff. So these are the inequalities, and if you solve the dual, and then you get that. So in some sense, this is one class which we can solve in finite arithmetic steps and with purely by linear programming. Okay? But there is a real problem with policy improvement in this case. Even though we think like that, what happens if both players can control the game? Okay? And let us take we were thinking stochastic games with discounted payoff have, according to Shapley, optimal stationary strategies. not pure stationary, optimal stationary strategies. However, if you move from discounted to average payoff, so let us take an example of an average payoff intuitive game. You have a girl, if I explain in the Hindu language, the girl's name is Bama. See, Krishna is supposed to be a Hindu god who was in love with lots of girls. Okay? In our language, lots of girls were after him. So Bama was one of those girls who was very jealous and wanted to grab him. And what Krishna says is, we will both meet in the celestial garden. Okay? In the celestial garden, but I cannot tell when I am coming. But it will be between 5 o'clock and 6 o'clock. Okay? One. This is one possibility. Another possibility is, we both meet at the celestial garden and we finish our dinner, and who pays for the dinner is the issue. But the two people, the girl as well as Krishna, Bama as well as Krishna should write on a piece of paper, I am ready for marriage. Both of them say, I am ready for marriage. Then it is over. Which means Krishna becomes a permanent slave to Bama. That means then onward, he has to take care of her daily dinner or whatever it is, paying the dinner cost every day. What is marriage? Marriage is nothing but you are spending money on the girl. Okay? So you spend the money for the rest of your life. That is the second possibility. The first one is, suppose he says, I'm not ready for marriage. And she also says, I'm not ready for marriage. Whenever he says, I'm not ready, and when she is not ready, but he should be willing to take care of her dinner cost on that day. But suppose he says, I am not ready. Unfortunately, she says, I am ready. Then, as a lady, he should be ready. The fact that he says, I am not ready, is an insult to her prestige. She says, I don't want to meet you again. You were my last date. So now onwards, I am going to the state of hell where I receive nothing. I take care of, I suffer. So this is the game. This game is called the big match, which was written purely in notations by Blackwell and Ferguson. You follow the game, it's more important to follow the game. Huh? But no. She's not. Then he doesn't pay anything to her. Okay? But if he says, I'm not ready, and she says she's also not ready, but on that day he pays. That's how it is. So you have three states: dating state, players choose between. The other thing, important thing is, what is the action which comes out? Whenever they both say not ready, they continue to meet again. Suppose if he says, I am ready, and she says not ready, still They meet again, but on that day there is no payment for her. Okay, she takes care of her own bill, like that. And the absorbing state with payoff 0 is the situation where when he says I am not ready and she says I am ready. Okay. The matching state is the state where he is hooked permanently. So I used to put the name player 2 as Joe and player 1 as Liz, my next door neighbor. So I used to show this to my next door neighbor so that they will enjoy it. Okay. Now, there is no stationary strategy for player 1. For Bama doesn't have any good strategy. The girls who are self-absorbed, ostentatious, acquisitive, okay, such people do not have a good strategy to play. But they have an epsilon good strategy, but unfortunately, that epsilon good strategy should depend on the history played till now. What actions were, how many times? See, you can see the big thing which can happen is the girl can initially say no. Her aim is to maximize only in the long run average. The long run average is never influenced by the first few rounds. So initially she may get nothing, okay, or she may get some payment, but those things don't count. But how many times this guy proposed, yes, I am ready for marriage, that measures certain amount of seriousness. And she feels this fellow seems very serious in me. Maybe I should take a calculated chance, to give a small chance to say, yes, I am also ready. You follow me? So that depends on observing not the previous day, but all the days so far. How many times he said, I am ready? How many times he said, I'm not ready? So this difference is a measure of the level of commitment he has. If it is positive, very high positive, then it's something like that. So if a stationary strategy F chooses action 0 all the time, player 2 can use the strategy tau. This is a highly non-trivial theorem by Blackwell and Ferguson. Okay. So the moment you notice that these games are never going to be solved in finite steps. Even finding the epsilon optimal is all hopeless. That's all I can say. And why? Suppose the girl says, I'm going to take a small chance every day. 0.0001. Okay? And then with 1 minus that, I say no, I'm not ready. If you fix this number, epsilon, and keep the same strategy, it is a stationary strategy. But it is not optimal. Because if it is optimal, you should be able to even tell the opponent, I myself do not know what I am going to do, but I can say with probability 1 minus epsilon, I am going to say no. With probability epsilon, I am going to say yes. That's all it says. Not that the player knows what action is going to be taken, but very high chance that I take no. If Bama does that, then what the other person can do is, you should say yes all the time. So whenever he says yes, and with a very high chance she is saying no, she is not collecting anything from him. She is paying the bill every day, more or less with a high chance. But suddenly, one day, because she has given a positive chance to select the second action, yes, I am ready, okay, with a positive chance, then what he can do is, no, he should say no every day. He should say no every day, but she is choosing 1 minus epsilon epsilon. So when she says no, when he says no, he has to be paying the bill. He has to be paying the bill large number of times. But suddenly, with strong law of large numbers, it is with probability 1, she will end up choosing this second action. On that day, when he had said no, she goes to hell. So it is not, no stationary optimal strategy exists for her. Okay. No strategy for player 1 can guarantee a Cicero expectation greater than or equal to half. Okay. These are technical. Okay. So in this, they came with a very ingenious idea. This Kn is the difference between number of yeses minus number of nos by the opponent. And then she is going to evaluate on the nth day how many times this difference, what is the difference number? And she chooses a large number n, and with this probability, she is going to say, I'm ready for marriage, and wait one more day with this chance. Then you can show that all those things. You can get close to half minus some delta. Okay. So in some sense, so the key question was whether any stochastic game in Cicero payoff has a value. So Mertens and Neyman proved every zero-sum 2% stochastic game with finitely many states and finitely many actions in each state have value satisfying the inf sup equals sup in over the set of all behavior strategies. Okay, on the collection of behavior strategies you have. This is purely a fundamental existence result establishing that stochastic games with Cicero payoff criteria have well-defined values and optimal strategies. No. No, this is nonsense. Values. Optimal, epsilon optimal strategies exist. That's what you can say. Because these are infant soup. This nonsense, optimal strategy. So we move on from zero-sum to non-zero-sum games. Fink and independently Takahashi extended Shapley's theorem to n% non-zero-sum discounted stochastic games, showing that you have stationary Nash equilibrium for such games. So then what happened was, we were again interested computing the Nash equilibrium, even for an ordinary matrix game, is a lot of work. Okay, it depends on the linear complementarity ideas. But when transition is controlled by a single player, with Parthasarathi showed that discounted single controller games admit Nash equilibria in stationary strategies, and they also possess order field property. So we could only show the existence of stationary strategies maintaining the order field property. That means if the data is rational, you should get such solutions also in rational numbers. Undiscounted single controlled games also have stationary Nash equilibria with order field property. So what is the theorem there? Let 0 less than beta less than 1 be the discount factor and be the number of states. What you do is player 1, the maximizer, is not maximizer, player 1, because here both are maximizers. Okay. F1, Fm enumerate all pure stationary strategies for player 1 and G's for player 2 and assume that the game is controlled by player 2 in all states. So you can define the n by n matrix game as follows. For player 1, you write down simply the sum of the immediate payoffs when the players use F's and pure stationary strategies stationary strategies F and G. For player 2, you write down the discounted payoff. For player 1, you write down simply the ordinary sum. For player 2, you write down the discounted sum. If xi star eta star is any mixed Nash equilibrium of AB, then F star is summation xi star I Fi and G star summation eta star J Gj form a Nash equilibrium. And phi beta F star G star is summation, etc. And this is part of the proof which goes on. In fact, in those days, I'm talking about 1981, at that time, there was no Excel or anything. We had a program called Lotus. So in that Lotus, I myself was learning what is Lotus slowly. If you make a small mistake, you start all over again. There is no correction mechanism there. You start all over again, throw everything and start all over again. That kind of a thing. So what I would do is, I would use the Lotus to calculate the approximate up to 8 decimals, something like that. And then call my colleague Novak, who was visiting me from Wrocław. So what would happen is, I give this is the original pure stationary strategy pair. All these numbers have to be computed for a discount factor of beta equals 0.9, I think, something like that. Similarly, compute player 2's total discounted payoff for each strategy pair yielding the matrix B. So the two matrices will come. And then you have to imagine, I used to give only the approximate up to 8 decimals of this 192 over 1613. So I would call him and tell him, I used to make the phone call, and the both sides, it is his problem to find what is the exact rational number which represents it. Okay, that's what he was doing, and that's how the solution comes. So the order field property is quite intrinsic here, and the computation is essentially solving for a Nash equilibrium for a bimatrix game. It's essentially reduced to solving for Nash equilibrium for bimatrix game. I had, see what happened to us in 1970. I was in Essex, University of Essex. And then we were with Partharthi, we were writing a book on some topics in two-person games. So I go and check the math reviews. And Bob Aumann had written a math review on Lemke-Hausen algorithm. He says it's going to be one of the most fundamental contribution to game theory. Then once I saw that, I should learn what is Lemke-Hausen. But Lemke-Hausen algorithm is written purely in an algebraic language. It took next 2 months for me to follow it. Okay. And then I tried to work out an example. But even though I worked out the example, but I was myself not efficiently using the Lemke-Hausen algorithm. But whatever it is, it's quite a fundamental thing. The linear complementarity is one of the most fundamental things within algorithmic side of game theory. So this is all about Lemke-Hausen algorithm. And our algorithm for LCP fails for undiscounted single controller games. Only for the discounted it works. And then Nash equilibria in the induced biometric game do not always correspond to equilibria in the original undiscounted stochastic game. Induced MDP inequalities. Maybe the way so there are several other results which are for special classes and mainly more on zero sum. For non-zero sum, we just do not have too many, even here, for non-zero sum. So the discounted arrayed games are solvable via LCP in finite arithmetic, linear complementarity. So we need, probably Professor Stengel would have been talking about linear complementarity. So if you had attended, then you may be able to appreciate better. So the discount, additive reward and additive transition is a key to the whole thing, which is the one order higher than perfect information case. Even for general all two-person zero-sum stochastic games, instead of zero-sum, non-zero-sum stochastic games, Nicholas Wheel proved the existence of equilibrium payoff for all two-person stochastic games. And Ilan Solon extended this to three-person absorbing games. For general n-person stochastic games with Cicero payoffs, the question is still wide open. And I had another student, Iji Filar. He came from Australia, and we were working only on single controller stochastic games. He asked at that time, what happens to the switching controller stochastic game? So that means in state 1, in states controlled by player 1, his actions decide the transition, in states controlled by player to his actions control the transition. This is more general than the perfect information case. And there also he proved that the game admits stationary strategies, optimal strategies in and retains also the order field property. So that means there should be algorithms to solve them. We still don't have one. We still don't have one. Whatever we have is very inefficient. Every n% arrayed stochastic game admits a pure equilibrium strategy. Reduced to n zero-sum games, for each player I, form the zero-sum game gamma I, in which player I faces the coalition n minus I, acting as a single opponent. The arrayed structure makes both reward and transition additive. And in a paper with Stuff Ties and Breeze, every zero-sum 2% arrayed game has a pure stationary optimal strategy for discounted as well as Cicero payoffs. They admit a pure stationary optimal pair with value function B. Each player now has a benchmark VI he can guarantee, and the coalition has a strategy that holds him to it. These are the ingredients of a threat. So it is a threat kind of strategy by which you bring the people to play. The moment player J deviates, the coalition N minus J switches over to punishing him as a group. Don't do that. Come back. Okay, behave properly. The strategy optimal against player J, warning him that he cannot hope for a Cicero expectation higher than what he was originally getting. Has a pure stationary optimal as well as for a coalition minus J. It's all depending on the arrayed structure also. So now you can write it and show it by all these inequalities. So this is what I said, of every 2% switching control stochastic game has an equilibrium payoff. All these things are only technical. One more. Maybe I should stop now, I feel. How much more time I have? Huh? 3? I would stop less than 3. That's good enough. Okay, because the positive stochastic game I want to talk next time. Okay. See, the whole problem is normally I am more confident on a blackboard where I can write something and write down the inequalities, etc. This kind of talk with overhead transparency, I'm not an expert. And even for this one, I had to depend on umpteen people, and my son would prepare the whole thing. I will write down on hand everything and send it, and he will put everything in this format. That's what was happening. And then you really do not know at what speed you can go. You can write down all those inequalities. But the problem with the inequality is, it is you really follow it, but you cannot communicate to the audience immediately. You can only see symbols. Okay. So the more important thing is to appreciate intuitive idea of that. Only the intuitive idea of what is a stochastic game and what is a. So the thing is, in ultimately any algorithmic side of it is to reduce it to a Markov decision process. And you have only two kinds of strategies which you can think about. One is policy improvement method, another is linear programming or linear complementarity method. For Nash equilibrium side, it is always linear complementarity. For other than that, for zero sum case, it is always something to do with either policy improvement or linear programming. But policy improvement is effectively like Newton-Raphson method. So it's in some sense, it's very close to Newton-Raphson method. So it is a much faster algorithm. Very often, it is much faster algorithm if you started close to the good strategy. That's what it is. Okay. Thank you. You have any questions, you can ask me. But
Maybe we can use it. Let's use it for a while. Does someone have questions? Who? Who wants to ask something? No one? Oh, okay, all right. So now we have a coffee break, and that's it.
Esse era qual?
Esse é o que estava aqui mesmo.
Ah, o próprio dele.
É.
Vou falar lá com ele.
Ele tá lá, ó. Ele tá ligado, mas alguém subiu no futuro. E aí, entendeu tudo? Eu vou. Eu vou.
Tá, vou tirar o microfone. Som. I, dois, teste. A, I. Som. I.
Davi? If Alexander Nesterov is here, Raghavan is looking for you. Okay? Well, now I'd like to call my dear friend and co-author, Davi Pérez-Castrillo, to talk about recent work of ours, the Tradewise-Core for transferable utility games.
So thank you, Marilda. It's an honor to be introduced by the boss of the conference. So thank you very much. So 12 years ago, I was here presenting a joint paper with you in this same room. So I am very happy to be back at USP and still presenting some new work that we are doing. The Tradewise-Core for transferable utility game. So the idea of this paper is to, typically when we analyze games in characteristic function form, and we try to obtain solution concepts or the core or values or something. So what we typically do is we look at the final payoff and then we check, right? Or we look at the coalitions and then, we don't care much about how the traders have decided to make coalitions or whether it's any process or something, but we just look at what can be achieved and we try to propose the share of the payoffs. This is satisfactory in many environments, but in other environments might not be so satisfactory. For example, one implication of this type of analysis is that it is often the case that the set of core payoffs is empty, for example, and there is not much we can do because we really don't go too much into how coalitions are formed or what's actually feasible or not feasible, etc. Right? So, and in this paper we try to use a little bit this idea to try to think about how coalitions form, and we are not going to propose any mechanism or anything to form coalition, but to think a little bit about how coalition form and when is it sensible that the coalition might or might not form, to try to address the question of outcomes for this type of games. So okay, this is way shorter than when I prepare. So. I'm sorry, something was cut while I transfer. So let me just explain, okay? So in the traditional, again, in the traditional idea of the analysis, what we try to say, we have in the von Neumann-Morgenstern environment, we have a set of players. The main decision about the players have to do is to form coalitions. We associate a payoff or a worth for each coalition that can be formed. You know, there's common knowledge about everything in the game, etc. And then our solution concept, possibly the most common concept is the core. So what is the core? The core studies stability through blocking. A payoff is stable if no coalition can guarantee its members a better outcome by deviating. So what we do again is we look ex post. So you propose me something, right? So you propose me a payoff and I say, look, does it belong to the core or it doesn't? But I don't care how we manage to get there. So we don't look at how the coalitions are formed. We don't know how this payoff is formed. We know that the grand coalition can achieve this payoff. We look at it and we check whether it is blocked or it is not blocked. So this is ex post of a process. Okay, so we don't analyze what will happen. And then our question is it really okay to just look at the final outcome? Is it okay just to, or shall we see what happened in between? Okay. Now sorry, again, I don't know what happened in my presentation. So our idea is to try to look at how coalitions form, and again, what's reasonable or what's feasible in reality, rather than only look at the final assignment. For this, since we are going to look at coalition, not necessarily the grand coalition, we are going to consider in this paper allocations. So what's an allocation? It's a payoff distribution, but also we want to know what is the underlying coalition structure that allows to achieve this payoff distribution. This was, the definition is not ours. It can go back to Ullmann and Maslow in '64. They call it a payoff configuration. Okay. And then the important thing probably the main idea of our paper is to consider what's actually feasible. So we consider feasible not everything. I mean, in the classical definition of feasibility, an allocation or a payoff is feasible if it's individually rational and can be achieved through the grand coalition. So the sum of all the payoffs is V of n, or less than V of n. We're actually only going to consider feasible a situation that can plausibly arrive, optimally arrive somehow. So that is a situation that can actually emerge from the cooperative behavior of players at a certain stage of the coalition formation process. Again, we are not going to propose any non-cooperative mechanism to arrive there or something. We are just thinking of situation in which, if a group of traders, we are going to call them traders, a group of people decide to collaborate to form a coalition, not necessarily the grand coalition, they will do so if their behavior is optimal. You see, so we are going to deal with general TU games, but many of these ideas come also from matching games. Right? So imagine when we analyze matching outcomes, we often don't see the grand coalition, etc. We talk about the pairs, we talk about the coalition, if it is many to one or many to many, etc. And here it's a bit the same. We don't need to focus only on the grand coalition. We can be talking about situations where the grand coalition didn't form, we have smaller coalitions. And so our main idea of feasibility is this, we're going to call it trade-wise feasibility. And this idea is based on, let's say, two principles. This is actually like one principle we can divide into two. The idea is the traders are going to behave optimally. So they will not do anything that they know they can stay there. Okay, so the first principle is no set of traders can profitably renegotiate among themselves. So if a coalition forms, it cannot happen that the subset of this coalition, or a coalition of several coalitions form at the same time, it cannot happen that the set of these traders, those people involved in the coalition formation, they know that actually they can do better, because if we know that we are going to make agreements where already a group of those can do better, this is going to, it is not feasible. This is not going to happen. These agreements are not going to happen. So this is not feasible for us. And similarly, we are not going to consider feasible those agreements where there is a group of traders that can do better by moving, looking abroad and say, look, there is this group of non-traders with whom we can negotiate in let's say, stable agreement later. So something that's going to stay. Okay, I will be a little bit more precise when I talk at the model. So the idea is that we look at the traders, and traders will not be involved in negotiation or in coalition formation where they know that is not going to stay there. Okay, it's not going to last. And we call this trade-wise feasible outcomes. Okay. You see that for those of you working on matching theory, this has some similitude or go back a little bit to the idea of simple matchings, right? So in the simple matchings is matchings in which, you know, traders cannot be involved with people outside, right? Which come back to Marilda's idea a few years ago. So, and then, sorry, I don't know what happened with my, I hope it's not a general problem with my transparencies because I don't have my computer here, but so we are going to define the core. We're going to call it the Tradewise-Core as the set of allocations that cannot be blocked in the sense that we cannot find a coalition that can form a new trade. I mean, if we form something, it should be something that is trade-wise feasible. So there is no coalition that can form a trade-wise feasible allocations and block the current allocation. This is going to be the Tradewise-Core. So what are the main results of this new definition? Every trade-wise feasible allocation that is not trade-wise, by the way, I didn't say, but in this framework, we can of course define what's Pareto optimal among the trade-wise feasible allocations. We can define the definition of an extension in the sense that, you know, we have an allocation. Can we add new coalition and still be trade-wise feasible? These are the three main results of the paper. Every trade-wise feasible allocation that is not Pareto optimal can be actually extended. So that means that we can keep the trades that have already been made and add new trades, still be trade-wise feasible. And we can do it in a way in which we finish in a Pareto optimal allocation. This is the first result. The second is that this trade-wise course, as I just defined, is always non-empty. And it coincides actually with the set of trade-wise Pareto optimal allocation, and it also coincides with the set of those trade-wise feasible allocations that cannot be extended in the way, again, I just mentioned. And finally, I guess we all like the core, right? So the core is a reasonable solution concept. I mean, when the core exists, it coincides with the trade-wise core. So we also like the core. What our solution proposes is a set of allocations that when the core exists, coincide with it, and when it doesn't, we propose something, which is the trade-wise core. Okay. I've been talking about allocation. Remember, you know, when we usually talk about the core or any other solution concept, we talk about payoffs. In here, we are talking about allocation, not only payoffs, but we can define, of course, hopefully I shall be able to do it, to define the core in terms of allocations and not only payoff. And I will be precise what is the relationship between core allocations and core payoffs. Okay. That's it. That was my introduction. I like short seminars, so I hope to finish not in time but early, so we'll have time to discuss if there are questions about it. So this is the model. Nothing major about the model. We have a set of players, capital N, with n elements. So we define the characteristic function form, V of S. This is the worth that is available for the people in S to be distributed. And of course, we are in a world without externality, so V of S can be achieved without intervention or without taking into account what happens outside the coalition S. We normalize so that not only the empty sets has zero worth, but also an individual has zero worth. This is just a normalization. Importantly, we are going to consider super additive games That is, at the end of the day, we are thinking about how coalitions form, and the formation of coalition. If we form a coalition, we can decide to also split among smaller coalitions. So we're going to consider that the game is super additive. Okay, so what's an allocation? Again, this is a partition, and it is a set of payoffs. So the first thing is the partition. We're going to call it an assignment. So an assignment is just the distribution of the players among coalitions. We're going to use the notation of sigma. Sigma for us will be an assignment. I'm showing this example because I will be using this example several times. This is so this is again with 8 players, 1, 2, 3, 4, 5, 7, 8, and an assignment is just a partition. So one in this case, 1 and 2 form a coalition, 3 remains alone, 4, 5, and 6 for another coalition, and 7 and 8 for one coalition. This is an assignment. We will say an assignment is optimal. It maximizes the worth of all possible assignments. Our game is super additive, so in particular, the grand coalition is optimal. But then maybe we're interested in situations in which other partitions are also optimal. Again, like in the assignment game, for example, right? I have a problem with this. I'm sorry. Let me check. I don't know what happened. I don't have all my transparencies, my slides. I checked the hotel. It was fine. Sorry. I guess I can get to the internet and find my slides. I am very sorry. This is the first time happening in my life. But it is complicated, no? So I should go to. Oh my God. But it's no, but it is complicated actually. How many functions? 32. I'm sorry. Okay, so I will talk on it otherwise. Okay, I'm sorry. I don't know what happened. I'll live with it. I think the only time it happened to me is that there was no electricity. I had to give the talk without the transparency. So I guess switching some transparency should do a little bit better. So let's try to do it. Okay, so we started with there was a game. This is the assignment. But actually, I saw an allocation here. It is like if it's an allocation. I don't know. It's actually switching because this slide was not before and it is now. An allocation. This is my next slide, so this is fine. So an allocation. Something is weird with the PDF. Actually, it's fine. I mean, again, I will manage.
Is it the PDF? Or you just
I think it's the
this? Instead of using this,
Okay.
just use up and down.
Okay. Here it is even the. No, this is fine. This is actually this thing. Okay. Thanks. Okay, let me at least refer a little bit to the literature. Okay, so I think it was this machine. Okay, thank you. I think you are right. Let me talk about the literature. I mean, at least 1 minute for the literature. So one of the things we do, I mean, I think our main contribution is to provide this, to propose this new definition of feasibility, and this definition of feasibility leads naturally to the definition of core and other definitions, right? But of course, our paper is related to the literature that extends the core in TU games. Probably the best well-known contribution is in bargaining sets. There are several papers proposing slightly different bargaining sets with the idea that people are forward-looking, and so some of the blocking is not reasonable. This is the bargaining set. A different idea from the bargaining sets is the extended core. So the idea of this extended core is, let's increase the amount of V of n, let's increase what the grand coalition can achieve. We share this grand thing. Now, if V of n is larger, then the core exists, and then we somehow tax the players after this extension so that we can repay this extension. And finally, the third extension is the positive core, which is called the positive core, which is somehow related to the idea of the nucleolus. So let's try to minimize the complaints of the coalitions. Right? So this, as our solution concept, as the Tradewise-Core, this extended core and the positive core actually coincide with the traditional core, with the core is not empty. Okay? So our paper also interested in this literature. So again, look at this, it works. So this is the game. Sorry, it was my fault. I didn't realize it. This is a game we are going to play with. So this is 8 players, and in this game we are going to consider one in which there are 6 productive coalitions. We are going to call them. Again, in the assignment game, there will be like pairs that can produce. This is 1 and 2 together. Get 3, 3, 4, 5 together get 3, 6, 7 get 3, 6, 8 get 3, 7, 8 get 3, and 1 and 6 get 1. These are the 6 productive coalitions. Now, any other coalition different from this can get worth just subdividing, if it is possible, in those productive coalitions. So, for example, if we consider the coalition 1, 2, 5, 7, then 1 and 2 can be together and produce 3, 5, 7 are useless here. So the value of the 1, 2, 5, 7 coalition is 3. If we get a little bit more complicated, 1, 3, 4, 5, 6, then 3, 4, and 5, they obtain 3, and 1 and 6, they obtain 1. So the value is 4, etc. Okay? Yeah, the super, right. Is correct. No, it is correct. It is correct. This is the superlative cover of the game in which only these 6 coalitions would have worth. Okay? This is correct. Okay, so we already saw the assignment for this particular game. Now, an allocation is again an assignment, so a partition, and a vector of payoff which is compatible with the assignment. What compatible means? Then a natural thing. If we have an allocation when 1 and 2 are together, and they can share 3 because the worth is 3, the payoffs of players 1 and 2 should be 3. This is compatible. So the payoff should be compatible with the coalition they are forming. Okay. So, for example, in this example, in which we had the coalitions 1, 2, 3, 4, 5, etc. First 4, 5, and 6, there was nothing because actually the coalition that produces value was 3, 4, and 5. So 4, 5, and 6 is the worth is nothing of this coalition, so they share 0. 7 and 8, they're worth 3, so they should share 3. For example, 1.5 each. This is a compatible payoff with the assignment that I just proposed before. Okay. Coalition structure. We call it assignment, but yes, there are many names for that. One is the coalition structure. Yes. Allocation is shorter, so that is why we chose it. Sorry, assignment is short. Okay. Now, given an allocation, sigma u, we're going to denote T of sigma active player. We're going to make a difference between active players, so people involved in forming coalition. These are people who took decisions concerning forming coalition. These are T of sigma. That will be our traders. This is where the nom Tradewise comes from. And U of sigma, which are the non-traders, those who are isolated in the assignment. And we'll denote sigma slash T of sigma, the set of active coalitions in an assignment. Okay. For example, in the running example, everybody actually was formed part of a coalition except player 3. So T of sigma n is just everybody except 3, and U of sigma n is 3, the player 3. Okay. Now the classical core, the core of NV, And again, we are going to name it in terms of allocation. So an allocation is in the core if u of n is equal to v of n and it's not blocked. Okay, so the worth of the coalition for any coalition is lower or equal than what the players get, the sum of what the player gets. This is the classic core. In the definition of the core allocations, actually the sigma almost does not appear. The only thing because we only look at the v of n. Okay. Now we consider allocation, core allocation instead of core payoff, but actually it's the same. It is the same animal. We have the same. In general TU game, we have the same property that we have in the assignment game, for example. Remember, in the assignment game, you have a stable assignment or core allocation. Then the assignment or the pairs are necessarily optimal. And actually, any stable payoff in the assignment game is compatible with any optimal matching. Okay, so we have this Cartesian product property. Right, where again you have on one side the set of optimal matchings, on the other side a set of stable payoffs, and you can mix them anyway because any mix it is a stable allocation. For TU games, the same happens in general. Okay, so if the core is sorry. Yes, this is the project of payoffs. Yes. So again, suppose the set of core allocations, again, for us, C is the core of allocations, and when we put this slash thing here, is payoffs, yes? So if the core is non-empty, then sigma is optimal. And any optimal assignment is actually compatible with any core payoff, okay? So this is the set of core payoffs. We will use this notation for payoffs always. And in general, without it, it's going to be allocations. Okay, so again, this is a nice property because at the end of the day, whether we talk about core payoff or core allocation, it doesn't matter. I mean, it is the same sets basically. Okay, the only thing is for allocation, we just can put together. You put together any optimal matching, and it's a core allocation. Okay? Again, in particular, n is always optimal, but we are also interested in situations where there are other optimal assignments. Okay, trade-wise feasibility, which is again is probably our main definition in this paper. The two principles I talked before is this, the two requirements for some allocation to be trade-wise feasible is no set of traders in sigma. Remember, this was our set T of sigma. No set of traders can profitably renegotiate among themselves. So it cannot happen that we are making an agreement that we know some of us will be interested in reneging from, okay? And the second, again, is the same, but we can also, we as traders, this is us, we are negotiating, we as traders, it cannot be the case that a set of us, subset of us, can actually renegotiate with people outside, offering them enough so that whatever comes is going to stay. Because then, again, we know that whatever sign is useless. So this is trade-wise feasibility for us. Now, about the second, the first thing is easy to understand, and I will show you, of course, the condition. Second is a little bit more tricky. So what do you mean by that? So about the second principle. So imagine we have a non-empty set of traders and a non-empty set of non-traders, inactive players, okay? So we have R is traders, is non-empty, R prime is non-traders. So imagine that these guys are thinking about blocking. So, when they make the agreement, they think, look, non-trade. Oh, sorry, this is a U. This is a U. You think it's a T, but it is a U. This is U sigma, okay? This is U sigma. Thank you. So it's traders and non-traders, sorry. And imagine that these people are thinking about blocking because what the traders get, you remember, no traders always get zero. What the traders obtain is actually smaller than the worth altogether, right? Now, if this allocation, if an allocation is trade-wise feasible, there should be no agreement between the traders and the non-traders to form the coalition S that satisfy that, first of all, makes R strictly better off, but at the same time, we have to make sure that it guarantees at least V of R prime to the non-traders, because if it guarantees less than V of R prime, we know this is going to stand, because if once we sign it, the guys sign, R prime will go away. So for the blocking to be, sorry? Getting zero now, but no, it's a little bit in a similar argument as we could talk about the bargaining set. You know, who is going to block with some group of people that we know they're not going to stay there anyways, because if whatever we sign is going to be reneged. Okay? No, V R prime is not zero. U of R prime is zero. But V of R prime is not zero. Yes, right? So again, so we want to make sure that to be blocked, something is, we're still not talking about blocking, but to be Tradewise feasible, it shouldn't happen that guys inside and outside can guarantee themselves something better off that will be stable somehow, that will stay. And that will stay, that means that first of all, we need to guarantee that R gets at least as much or better than they used to be, than they are now. But considering also that the outsiders are going to get at least V of R prime. Okay. At the end of the day, all these arguments say that, okay, this is stable if whenever a coalition is thinking about blocking, it must be the case that the worth of the grand coalition of S is not enough to cover what the traders are obtaining and what the non-traders could obtain. Yes? This is our, sorry, the first, sorry? Yeah. Yes, yes. No, but that's going to be the next, yeah. This comes from the first, yes, sorry, yes. Sorry? So again, this is the condition that needs to be satisfied whenever a coalition between traders and non-traders can potentially, or is thinking about blocking the allocation. Okay, so these are the formal definition. An allocation is trade-wise feasible, feasible if this is the first condition, right? So no internal, this is the condition I already explained, but I didn't put formally. No sub-coalition of traders can do better off on their own. So UFS is always larger or equal than V of S. But in addition, for any coalition of traders and non-traders, needs to be the case that V of S is smaller or equal than this thing. Okay? This is the definition of trade-wise feasibility. And again, the idea is that something is trade-wise feasible if people are behaving optimally in the sense that they know that whatever sign there, this is not going to change. Yes, one corollary, the condition requires smaller or equal, but of course this is going to be equality, yes. Okay. So the idea, the definition of trade-wise feasibility does not require equality, but indeed with operative gap, this is inequality, yes. Yes? Okay. Can you move on? It's equality, yes. Yes. Okay. Okay, so 2 examples. This was our first example, right? Remember? 1 and 2 were together and actually get 3. 7 and 8 get together and actually get 3. And for 4, 5, and 6, the worth of the coalition is 0. So this is not trade-wise feasible for many reasons. I mean, you can find many, several instances of several reasons why this is not feasible. In particular, this is not feasible, for example, because let me check. 6 and 7, right? 6 and 7, who is here, right? They could get together. They would obtain 3. But 7 might think about going with 6 because now the worth of 6 is actually 0. So what this coalition 6 and 7 get, this is 1.3. This is the payoff that it is receiving, but it's lower then they could get together, which is 3. So this is not trade-wise feasible. On the other hand, this other allocation is feasible. So 1 and 2 together and the other isolated is feasible. Because none of the traders, again, this is a little bit similar idea of what we have with simple matchings. We look at the behavior of the traders and whether the traders have an incentive to deviate or not. In this case, no trader has an incentive to deviate. There is nothing they can do with any other coalition of non-traders that would guarantee the non-traders the value, at least the value of their coalition, and that it would improve their payoffs. This is no problem because it's 3, 4, and the coalition that provided worth was 3, 4, and 5. Okay, so for 4 and 5 is worth nothing. Yes. 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 Yeah. Yeah. Okay. 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 So if 4, 5, and 6 is not a coalition, they are all isolated. And now what do you mean? Is 6 can go? No, it's still not feasible, no. Okay. Okay, so imagine these 4, 5, and 6 are not traders, right? Then what happens is that 6 can go with 7. Now, if 6 go with 7, the worth of the coalition 6, 7 is 3. What 7 is getting is 1.5, and what 6 can get on his own is 0. So the value, the worth of the coalition 6, 7, which is 3, is actually larger than the sum of what 7 is getting plus the worth of the coalition 6. Since this is larger, this would make this. In this case, it doesn't because 6 is 0. Okay. Again, yeah. No, imagine the example you say. Imagine 4, 5, and 6 is they are all isolated, okay? They are not traders. So the only two, so consider the same allocation. The only thing is that 1 and 2 are together and share 1 and 2. 7 and 8 are together and share 1.5 each. And 3, 4, 5, and 6 are isolated players. Okay? This allocation, this is also not trade-wise feasible, okay? For the reason I said before. Yes? Okay. Yes? Okay. Correct. Because they have no. What they could do? Yeah, but the thing is, we're looking at traders. You know, when you sit, you don't have to worry about what the other people are going to do. You are going to. Our idea is you form coalitions, and then at the end you look whether what we are going to do is going to stay or is not going to stay. You may think, no, but this is not stable because other people are going. Look, if whatever we do is going to stay fixed, whatever the others do, we are going to do it, and this is feasible. At the core, sometimes we care about, okay, this is not stable. Whatever arrangement we have made is not stable because other people can do other arrangements. Look, I don't care. We can still do our arrangement, right? This is the thing, okay? So this is why traders, when they take decisions to form coalitions or not form coalitions, they look at themselves. They don't look at whether outsiders can or cannot do, as long as it doesn't influence what they are actually doing, the arrangement they're actually making. With the definition of the feasibility, you can define block as usually. So the condition U of S is smaller than V of S in our case is not enough because you want an allocation to be blocked by another differentiable allocation. Okay? So we're going to require that an allocation, a feasible allocation, or a coalition blocks an differentiable allocation if there is another differentiable allocation that this coalition is part of that actually block this first allocation. Again, I will make the definition precise. One thing to remark is that given that the coalition we are checking whether it is a core allocation or not is divisible, actually when there is if there is any blocking, you can show it's actually a blocking by outsiders. It cannot be blocked by any coalition with traders. So given this, the definition of T blocking is that, so consider a differentiable allocation and a coalition. We say that a coalition T blocks a differentiable allocation with another, through another differentiable allocation that can be different. So this is a different assignment and a different payoff. If the guys in S can guarantee themselves more than U of S, and the rest of the structure doesn't change. Okay. Feasible allocation is in the Tradewise-Core if it is not blocked. And again, we have a set of Tradewise-Core allocation and a set of Tradewise-Core payoff with the same example as before. Okay, so we have a set of payoffs and a set of allocation. So in this example, for example, this is probably all of you have already noticed. This is an example with empty core. Remember, 1, 2 get together 3, 3, 4, and 5 could obtain 3, 6 and 7 also get 3, 7 and 8 get 3, 7 and 6 and 8 also get 3. So in this example, there is no core because then there is no way in which 6, 7, 6, 8, etc. form without blocking. Okay, anything that 6 and 7 do can be blocked anyways. So this is a situation with an empty core. Now, what we propose as a solution is, look, 1 and 2 form, 3 and 5, 3 and 4 form. There is no way in which a coalition would block this allocation involving 2 and 3. So externals can block, but whatever they do is not credible, is not divisible. And there is no way in which you can block involving traders. So traders can form their coalitions. They can be happy forever. They know nothing is going to change their situation. And 6 and 7 stay isolated. Okay, so this is the Tradewise-Core in this specific example. Okay, we can have definition of extensions. This is already late. So we have definition of extension. We can, you have a trade-wise feasible allocation. You can extend it by adding coalitions to the already existing, assignment, etc. And then we say that another trade-wise feasible allocation extends the previous one if coalitions are better and the payoff for the existing coalitions don't change. So you just add coalitions to the existing situation and running. This is to produce something that is different for extensions and for the core is tricky. So this is the same thing is useful here. And again, we can talk about Pareto improvement. An allocation Pareto improve another one if the payoffs are better for the better or larger or equal with at least with equality. So this is a Pareto improvement in terms of payoff. And then we call trade-wise feasible allocation trade-wise Pareto optimal if there is no Pareto improvement. So there is no way in which you can improve the payoffs through another trade-wise feasible allocation. So this is the 3 results. And the first one is that there are the 3 results actually I show you. Every trade-wise feasible allocation that is not trade-wise Pareto optimal can be extended. So that means that whenever an efficient trader has not been reached, you can continue somehow the process until something which is Pareto optimal is reached. So this is based on two observations, but I think I'm running out of time. So this is, let's say, two lemmas. The first one is that if you have some trade feasible allocation, you can find another trade feasible Pareto optimal allocation where the payoffs are strictly better for the players. And actually, once we have a Pareto improvement, you can actually, it's a little bit the same as this Cartesian product property, you can make it so that actually the previous assignment remains. Second result is that Tradewise-Core is non-empty and coincide with the set of Tradewise Pareto optimal allocations. So somehow the Tradewise feasibility guarantees some this consistency between incomplete trades. So Pareto optimality guarantees that nothing is going to be blocked. And at the same time, if nothing is blocked, it's actually Pareto optimal. So our idea is, so where we envision this, again, this come from the matching literature. So you start making coalitions, right? So this is a process that can lead to our Tradewise-Core. You know, you start from everybody's isolated and people start thinking about forming a coalition, then maybe 1 and 2 get together and say, look, we can make a coalition, and given the coalition and given the payoffs we're having here, nobody will bother us ever. So they make a coalition. Once this coalition is made, also 3, 4, and 5 can get together and form a coalition, and they know that whatever happens later, whatever other people are going to do, nothing will prevent these people to stay there. So they form a coalition. And this finished because whatever other coalition that can be formed here that is necessarily among the outsiders will never stay there. So this is our proposal. This is a solution where this is an example where the core is empty, and this is the Tradewise-Core. On the other hand, as I already mentioned, when the core is non-empty, then both solution concepts actually coincides. Okay, the set of allocation coincides, and also the set of payoffs coincides. Why do they coincide? Because actually, core allocations are, if core allocations are exist, these are going to be the final step in any process of coalition formation. We're going to make it there, okay? And actually, you can take any trade-wise feasible, when the core exists, you can take any trade-wise feasible allocation and actually follow the same path as any core allocation you may think. So what we actually do is we construct from a trade-wise feasible allocation another, which is actually in the core. Okay, so again, so this is somehow inspired by how coalitions are made in matching models, in assignment models, or in situations where coalitions actually are made. We consider feasibility as a trading process. We are not going to look at the game only at the end, but we can look at what people can do without arriving to the grand coalition. Efficient trading emerges endogenously. The Tradewise-Core is a solution concept, but it's always non-empty. And actually, again, we also like the core, but whenever the core is non-empty, actually the two solution concepts coincide. Okay, so thank you. There were questions before, so thank you.
So up to now, we are gonna have the mini course 4 with Professor Moulin, Fair Division, the Allocation of Private Goods in Common Property, here in Auditorio 1.
change the file. So can we locate the file, or maybe put the new files in? Yeah. Yeah. So I can take this one off. How do I? Ah, yeah, yeah. It's good. Yeah. Thank you. And you tell me the time when you. Huh? Okay. At 5 minutes before, or 10 as you want. I mean, it's. All right. Good morning. I will continue now on this discussion of fair division, and starting with some discussion of incentives, and something which is not necessarily known to many of you that I call the Hurwitz theorem. It has to do with strategy proofness, and it is similar. It is one of those important impossibility theorem that we find in mechanism design when we impose the strong condition of strategy proofness. What is interesting, in fact, is that it's a theorem between quotation mark. I mean, I call it quasi-result because it was suggested by Leo Hurwitz in 1972 with an approximate proof. You know, one of these proofs where, I mean, never mind. I mean, the fact that there were some topological things that were not very clear, but so people got the intuition and they realized, okay, there is some serious impossibility problem here, which is that in the context of Hurwitz, we had two agents, two goods, with an initial endowment, which was not necessarily the same, and Arrow-Debreu preferences. And then the result is that there would not exist any mechanism, any trading rule, mechanism which, based on the endowment and preferences, allocates the resource. There would not be such a rule which would be efficient, Pareto optimal, strategy proof, and respect voluntary trade, namely the trade is voluntary, so you get at least as much utility as from your initial endowment. So in our context, of course, the initial endowment should corresponds to the equal split of the resources, and the voluntary trade we call the fair share constraint. Right. So this is the contradiction that we have. The surprising thing is that you can certainly not, on the one hand, deduce that result from the Gibbard-Satterthwaite theorem. And in fact, it is a much, much more difficult enterprise to prove it. It was started by Lin Zhao, who was showing kind of dictatorship results in the context of a small number of agents, etc. And look at what happens. It took Serizawa until 2002 to finally have a clean, very beautiful shape for this result, which of course was not restricted to 2 agents and 2 goods. It's any number of agents, any number of goods. And you see, I mean, you have two impossibility in addition to Pareto optimality and strategy proofness, whether you want to add the very basic property of equal treatment of equals, which is, you know, like the ancestor of any fair division constraint, or whether you want to add the fair share, each time you can't. Okay, so that's very nice. And of course, I will not even try to start with the description of the proof. I just want at this stage to make a remark which came a little bit later by, and it was a remark that comes from a computer scientist. I mean, there is a group of computer scientists in which the senior author is Scott Schenker, a former co-author of mine, who is a very important figure now in computer science at the interface with economics, who made a simple remark. When you look at the technique behind it, and it's very simple, as you will see, is the fact that if you specialize to a very particular subdomain of not even Arrow-Debreu, but also Gale-Heisenberg, I mean the subdomain of Leontief utilities. You remember, I mean, Leontief utilities is the context where all the goods are perfect complement in your utility. So typically, for instance, if you have 2 goods, your utility for a pair X of good A and Y of good B would be the minimum of X divided by a certain fixed coefficient and of Y divided by another fixed coefficient, minimum of X over 2 and Y over 3, this sort of thing, as we had in some example. So he noticed something that had totally escaped the attention of economists, even though there was always a lot of interest in designing strategy proof rule, that in this context, if you adopt those two, any one of those 2 methods called the egalitarian equivalent, either along the diagonal of the bundle itself or some fixed direction, they are perfectly group strategy proof. And of course, in particular, also efficient and satisfy the fair share. I mean, if you take the one along the omega, and everything works well. Everything works well with the provision that you respect efficiency to the point of always throwing away goods which are useless. So when you look at this statement, it sounds that it should be complicated to prove, and in fact, it's very simple. I will give it to you almost as an exercise. I mean, I don't want to spend time on it, but you have to realize that in order to compute the egalitarian equivalent allocation, it's a very simple question. Okay, so suppose we have, let's say, 2 agents, and we want to achieve a level lambda of a fraction lambda of the total amount of goods, and give to everybody an allocation in which their utility is the same as if they were receiving a certain fraction lambda of all the goods. Okay, so think of this. Think of the good, the reference good, as if you have only two individual goods. I mean, as lambda, because there are two goods, you need to give lambda units of each. Okay, and lambda will be bigger than 1/2 if you have only two agents, or bigger than 1n if you have n agents. Now, in order to make that feasible, what do you need? An agent who has to achieve a certain utility level will tell you, okay, I take my optimal combination of goods, which is along my line, the line where they are in the fixed proportion, and I go exactly where I should go to achieve the utility lambda. So I just move along this line. Everybody does that, and you know whether or not the level lambda is feasible by simply summing up all these allocations and checking whether they are feasible or not. So what happens generically, and of course this is enough for the main argument, generically when you increase lambda on every coordinate, on every good, what you need to have increases, and at some point you hit the constraint that you have exhausted all the commodities. But in fact, you expect that it's going to be a single commodity that will actually hit the constraint, just by the genericity assumption. So at that point, it becomes a problem of dimension 1. At that point, especially if you if you make sure that what you give to the other agents does not make any use of these extra goods, because now we have extra goods on the other goods which are not hitting the constraint. You have extra goods that can be dispensed with. So if you make sure not to use them, no, just to put them out of the economy, now you have this single problem, and it becomes a very elementary exercise that if at that point, given that you will receive the fraction that was corresponding exactly to lambda, and you try to get an extra share by claiming that you need more those commodity with respect to what you get before. In fact, you will not, because of a simple computation that, I leave you as an exercise. The main thing here is to realize that everything now happens in the division of that single commodity, and claiming that you need it more will not actually increase your share, your real share of utility. It's a really two-line argument. Okay, and again, I don't want to spend time too much. In this context, of course, if you were to try to apply the competitive equilibrium with equal income to this Leontief context, of course it works and it's well-defined, unique, etc. But it certainly is manipulable. Okay, so that's a little remark. I mean, no other subdomain of the Arrow-Debreu domain, or even the Gale-Heisenberg, is known to have this kind of property. I mean, so it's a little bit of a curiosity. Okay, so now I want to start with the main topic of this lecture, which is what happens in the basic model of fair division that we consider when the things that we distribute are still infinitely divisible items, but those items are not necessarily goods, not necessarily entirely bad, and in fact can be a mixture of both. So now what we have preferences which are still continuous, convex, and will also satisfy, restricted by the monotonicity property, so that we can apply potentially the Gale-Heisenberg theorem. and but the mana is not disposable, and sometimes this is bad news for at least some of the agents. Okay, so I will start to give you to make you familiar, because now we're gonna redefine the model of competitive equilibrium with equal income in this context, and it's gonna take a little effort of notation. So that's why I want to start by a simple case, which is not exactly a special case, but is very indicative of what we're going to be doing. And it's a model that probably many of you, but not all, I suspect, know. It's a very simple model due to Sprumont, in which this time we share only one unit of indivisible item, non-disposable item. I mean, not one unit, but omega units of one non-disposable item. And each preference is convex on the interval 0 omega. But convex here, not necessarily monotone, essentially means up to some strict versus indifference case. I mean, essentially this means we have single peak preferences. In effect, you could have single peaks with certain plateaus and so forth, but let's forget about that. Let's just say that we have single peak preferences over the share that you receive, okay? And many simple examples of that situation. I mean, that's the point here is to remember that we will be able to deal with the problem entirely based simply on the information of the peak of each preference, the ideal amount of consumption. Okay, so Pareto optimality in this context is very simply described. There is two situations. The item can be, the omega items, the omega units of the item can be over-demanded or under-demanded, or demanded in exactly the right way. If the sum of the peaks is bigger than omega, it means that ideally the amount that they would like to consume exceeds what's there. So now we need to ration those who ask too much. And if the sum of the peak is less than omega, this time the item is under-demanded, and you need to give more to those who wish to take too little, okay? And it's clear that you cannot have in the same economy, somebody who is rationed and somebody who actually gets more than he or she desires, because that would be inefficient. You could simply give more to the one who wants more and give less to the one who wants less. So that's the description of efficiency. And it's easy to check. I will skip it. I think, well, maybe I have a simple example. That the natural, intuitive, proportional rule, where, because we are in the positive interval 0 to omega, so we divide omega in proportion to the peaks, which gives a same rate of rationing, fails actually everything that we are interested in, the fair share, the envy-freeness, and the strategy proofness. The example is like this. Three agents and 3 units of commodities, right? And agent A wants 1 unit at the best. That means, I remember from the definition of single peakedness, it means that the preferences of agent A increase when her share increases up to 1 and then start to decrease systematically. The peak for B is at 2 and the peak for C is at 3. So the proportional allocation 1/2, 1 and 3/2. The fair share is violated for A and B because A and B receive, A receive 1/2, right, with a peak at 1, but the fair share for A is, well, it's UI of 1, right? And it could very well be violated for. For A, it is optimal to get exactly the fair share, but you don't get that with the proportional. And then you also check easily the violation of envy freeness and strategy proofness. It's clear here that if you are one of those like A who gets less than their peak, you want to inflate, and it's also inefficient. Yes. Yes, yes. That's right, that's right. We don't make any specific assumption on it. It could be anything. When if my peak is at 1 and I compare 1/2 and 3/2, we don't put any restriction. It could be that 1 is. Yes, yes. But for instance, if you look at at agent A, agent A receives 1/2 and sees agent B receiving 1. So agent A is envious because we know that level 1, the share 1 is the best for A. And, you know, it's also not efficient. I mean, it's completely. And this model has been studied extensively since the initial Sprumont paper, because it happens that here there is an absolutely canonical and totally compelling mechanism which satisfies everything we need. It's the so-called uniform division rule. What's the uniform division rule? If you want, it's the natural egalitarian idea that we can apply here, but it's not egalitarian in the sense of egalitarian equivalence. It's in the following sense. So that will become precise soon. Okay, so let's define the rule, which is defined by two different formula, whether you have over demand or under demand. If you have over demand, what we will say is that there will be some threshold, some benchmark level such that you can at most obtain that benchmark level, except that if you happen to have a peak, an ideal point below the benchmark, then you are entitled to get your peak consumption. And why is that good? Is precisely because we have under demand. That means some people will have to be rationed. And if you happen to want less than the benchmark level, you are helping them by taking less, which happens to be your peak. So therefore, the formula is that your share Zi will be the minimum of lambda and pi I, where lambda is solved, is found by solving the equation sum of the mean of lambda pi equal omega. Okay? And similarly, when you have under demand, you have a minimal threshold lambda that you must consume. But if you happen to want to consume even more, you are welcome. All the others who potentially would have to do more are grateful to you. And that's also efficient. So this time you solve the max. And as you will see, this can be all at once interpreted as a CEEI. This is in fact a competitive equilibrium from equal income if we take the position that this is not a good, could be sometime a good at some level, sometime a bad, and therefore the price could be positive or negative. Okay, so let's to reinterpret that. I mean, let's say that the over demand. Okay, P equal 1, budget equal lambda. All right, okay, what does it mean? So suppose this is an example where you have my 3 agents with the same as before, with their peaks at 1, 2, and 3, the 3 agents A, B, C, but I don't need their names anymore. and I have to divide 4 units, right? So I'm going to put the threshold at lambda equal 3/2, because you see at lambda equal 3/2, this is a case, of course, where the good is over-demanded. In total, they would like to consume 6 units, 1 plus 2 plus 3, but there is only 4. So the threshold at 3/2 will allow agent 1, the agent with peak at 1, to consume exactly her peak, because it's less than the threshold. So she consumes 1, and the other 2 are constrained by the threshold at 3/2, and they each consume 3/2, and in total we are exhausting the what there is to divide. Here we think of that as a competitive equilibrium where the price is 1 and your budget is 3/2. And with this price of 1, budget 3/2, you are not obliged to spend all the money. You can spend at most the money, right? And therefore, if you are agent A, you don't buy all of it. You just get 1, okay? And the others, on the contrary, they spend everything. Now, if you have under demand, where, for instance, omega equals 7. 7 is what we need to consume, but in total, they would like to consume only 6. Now we're going to have a negative price of -1 and a negative budget of minus lambda, which will mean, I mean, we will still be maximizing utility over the share such that minus Zi is less than minus lambda, or if you prefer Zi bigger than lambda. So the negative price means, you know, I need you to get some transaction there, namely to pay the price -1 for as much as you want, but at least the level lambda. So now it's a price which forces you to buy, to eat at least lambda, and that's exactly what the rule says. Okay, so this is a simple example in which the option of having a negative price immediately help you to interpret the solution as a competitive one. So the theorem is that this rule has all the nice properties that you want. It's group strategy proof, Pareto optimal, fair share, etc. I mean, it's everything you want. I just cite here one characterization, but there are many others because the literature has been in overdrive over that for some time. Okay, so this was a simple problem. So now let's look at the not simple problems. Two or more items. All right. An item can be a good or bad at different level of consumptions. I mean, it's the single peak things, right? I mean, for a while you prefer to have more, and then after you reach the peak, you prefer to have less. An item could be a bad for some agent and a good for some others. And a combination, an arbitrary combination. Examples, I mean, there are many examples where it's natural to have some good and some bad things to divide. For instance, typically dissolution of a partnership, you know, when you have assets and liabilities, and, you know, some of this you don't want. Or simply you divide commodities such that you have single peak, so both good and bad, etc. Okay. So what is the technology? I mean, okay, yeah. What is going to be the domain? Yeah, I have to be clear that I'm staying exactly in the same framework as Gail Eisenberg from the standard case of goods before, and the assumptions are still just a tiny bit easier here to have immediately a concave utility rather than a quasi-concave. But as you perhaps know, I mean, the difference is really minuscule. But same thing, we are consuming in the positive orthant. Utilities are continuous, concave, and homogeneous of degree 1. So for instance, if you have linear utilities, it could be the, straightforward linear with positive or negative coefficient, or it could be something systematically negative, or mixing, sometimes negative, sometimes positive. I mean, it's it's restrictive, of course, but still allows you a lot of stuff. Okay, so what's the definition? What's the definition of a CEEI? So notice from the previous example that in that example, you had to have two different interpretations of budgets. I mean, if the price becomes negative, your budget is negative, right? If the price is positive, the opposite. So that's why now, when we speak about competitive equilibrium, equal incomes, the price P is a vector which is in RA with no particular restrictions, right? Could be even zero, I mean, but of course zero would mean that it's feasible to get everybody his or her best consumption. I mean, it's okay, it's not but the budget that you will get, we will normalize it for, it's easier to read like this, at -1, 0, or +1. So -1, +1, you can think of it of the case of, somehow over demand, under demand and somehow over demand for +1, but it's a bit more complicated because different items can have positive price, some other negative price. Okay, so now the demand is defined, the competitive demand is defined exactly as before, right? I mean, you have to choose in your budget set, and your budget set is, as before, the set of allocations which are non-negative because these are consumptions. So the set of items that we consume, they are in non-negative quantities, but they are constrained by PYI less than or equal to beta, which could mean if some component is negative, this could force you to consume some amount of that bad for you because you have to meet the budget constraint. Okay. Now there is an extra assumption that we need to make, which is that if in the demand set you have multiple choices, you want to eliminate the possibility that supply equal demand at an inefficient level. And this can happen because of the sign. I mean, it's not a big issue. And in fact, it's easily taken care of by simply saying that in the demand set, in this argmax set described above, the agents minimize the wealth. Okay, so technical assumption. I mean, this one, we cannot do without. We call it the parsimony assumption. All right. This is to eliminate some potentially inefficient allocation, but will not prevent the existence of an efficient allocation, of course. All right, so I need to give you some definitions because everything here turns around that. So please bear with me. So now I have my problem, and my problem is given. I have my utilities and my commodities. I don't have any price at the moment. I'm just looking at the set of agents N+. That's the set of agents which, at least from the pile of things that we have to consume, can find something valuable. So you see, it's a very, there exists, I'm just asking for agent to be in N+, that there is some allocation in which we can give something good to this agent. So essentially, and then so we call them attracted to the mana, right? They are not satiated at 0, for instance. But as soon as there is a bit of something which is good for them, they are happy. They are in N+. And N- are the opposite agents. They don't like anything in the manner, right? They, whatever you give them, whatever part of what you have to divide, which is the box from 0 to the vector omega, it's always negative. So, of course, there are problems in which everybody is N-, like we divide only bads. Problems where everybody is in N+, like we divide only goods. And the reason we have that is now, of course, we combine, so it could be that these two sets are non-empty. All right. Now we have the set phi of feasible utility profiles. Okay, I don't need to define, but it's I'm looking for all allocation. I transport the allocation by the utility profile in the space of collective utilities. And now we have two cones which are cones of utility. Okay, so the first one, gamma, is the cone where you are giving to the potentially attracted agent, to the mana, some non-negative utility, and you are not giving any disutility to those who could never like anything in the mana. So that's good. I mean, that's a nice situation. If the pile is such that I can make some people happy and those who can never be happy stay at 0, that's fine. I mean, I did as best as I could. And then I will need to have the relative interior, gamma relative interior. And this will play a critical role in the decomposition. Okay, we're almost there. Almost there. So what we do is we partition, we make a problem in the set of partitions. Sorry. We make a partition in the set of problems. I don't know why. Okay. We distinguish 3 types of problems which exhaust the thing. And this has to do with whether the set of feasible utility profile intersects this good cone gamma, in particular, intersected in the interior of gamma. So if you have the situation where goods overwhelm bad, it means that it's possible, since you are in the positive, in the relative interior, we strictly make everybody in N+ receive a positive utility, so they get something, and the other gets nothing, those who can never get anything. So it's really good. I mean, and so even though they are bads, none of the N- agent will consume them. They will all be consumed by the N+ agents, but the bads are not that bad that they cannot be overwhelmed by giving them enough goods. Okay. The negative case, the negative problem is when we cannot do that. Is that whenever you have a feasible utility profile, this profile can never be in gamma. So either some of the agent in N- will have to consume something and therefore be unhappy, lose vis-a-vis the initial situation, or some in the N+ will not get a positive or 0 utility, so they will have to suffer. So somebody has to suffer, right? Either in N+ or in N- or in both, right? So in that case, we say that the bads overwhelms the goods. I mean, because there is no way to make everyone happy in the minimal sense that they don't lose any utility vis-à-vis before the problem. And finally, the limit case in between the two is when the intersection exists, but it coincides with zero. That's the case, the only case that is left. Goods and bads are exactly balanced. And with that partition in mind, now we have a way to reformulate the Gale-Heisenberg theorem in the following sense. One last definition before is the notion of critical point of a function over a convex set. When we think, so now we are getting close to the Gale-Heisenberg, so we're going to do some Nash maximization, at least sometime, maximizing a Nash product. So when you maximize the Nash product, your idea is that in the set of, over the set of feasible utility profile, you maximize collective utility, and then, of course, the set of utilities which are giving you that level, that critical Nash product level, will be tangent to the set of feasible utilities. And here what happens is that there will be a similar story, but the indifference curve of the Nash product or whatever function we would maximize would be not tangent, but would hit the set of feasible utility as a critical point. And the critical point simply means that the function in at the point x in C, the critical point of f is a point where is the fact that x is a critical point of f is because the upper contour of f at x has a common supporting hyperplane to the one to C. I mean, and so you look at the upper contour of the function you maximize, and you observe that there is a supporting hyperplane of x of C, sorry, such that they have the same direction. They are the same hyperplane, right? And the upper contour has the same support, meaning that in fact the upper contour can cross inside the set. You will see. I mean, there will be figures, but I prefer to show you the figure in a moment, right? Okay. So here and below the inequalities are just those of the supporting hyperplane. And one instance where you have this situation, but it's not the only one, is the one where you have a local maximum of f in C or a local minimum. But there are also cases where it's like in the dimension in function of one real variable, you simply say that the tangent is a point where the tangent to the function is horizontal, but that the function can cross the horizontal. Okay, so time to give the result. And this explains why we still find a very strong, very close relationship between the CEEI allocations and the Nash product of utilities. So suppose the first statement is what happens when your problem is positive, when it's possible to make all the n plus agents happy and not to harm any of the n-1 agent. Then in this case, the CEEI does exactly that. This is the case where phi intersection interior of gamma is non-empty, and your CEEI will find a point in there which maximizes the product of the utilities, Same. So really, this first case is exactly the same thing as we had before, except that we have put aside the negative agent, the N- agents, who basically can never benefit, and we have been able to spare them without giving them anything extra, but at least they are spared, and over the rest of the agents, I mean, they have to absorb the negative part, but they do that, and we still maximize the Nash product over the this cone, the intersection of this cone with phi. Okay, so that's the positive problem. Now, and notice also that in the first case, the budget is going to be positive, and the price positive. You see, the price is positive and the budget is positive. Okay, all right. So, second case, the problem is a negative problem, right? So now the allocation will be competitive if and only if it is a critical point of the product of utilities, but not utilities, absolute values of utilities, because they could be positive or negative. And if you start doing multiplications there, the maximization makes no sense. And indeed, you don't maximize, you just say it's a critical point that belong to, you see, now what you are doing is you are finding a critical point of a kind of Nash product, but in the area where everybody is contributing, because we are now in Rn double minus, meaning that everybody is suffering a bit. Those who are potentially happy with some of the good, those who are never happy, everybody, all utilities are negative. So it's again very fair. I mean, you know, in the first case, it's very fair because all the positive people get some benefit, and the others, they can never be happy, but then we are not harming them. But now it's the opposite. So then the budget is null, and the allocation is competitive if and only if the utility profile is zero. Because this is the case where, as you will see in the figure in the second, you cannot give any positive benefit to everybody, so you don't. But you can also actually guarantee zero. How much time do I have left, please? Oh, okay. All right. So a mixed mana is good news or bad news if and only if the problem is positive or negative. But for a positive problem, all the good stuff of Gale-Heisenberg is preserved. I mean, now, in particular, uniqueness of the competitive equilibrium, continuity in the parameters, so forth. For negative problem, and that will be the key issue, the fact that really problems with bads are inherently, and for reasons that are not trivial to get an intuition for, are different. So you will see there is a multi-valuation issue, which in fact is large. I mean, it's a big problem to think about those, but it still remains welfarist. It still remains that if you give me if you draw for me the set of feasible utility, I can tell you what the solutions, these solutions are. Okay, so now for an example, all right. An example is fairly simple, but well calibrated to give you a good intuition. You have only two agents and three goods, A, B, and C. And A and B happen to be bads for everybody. But these are linear utilities, right? I just give you the marginal utilities. So A is bad for both agents, more for 2 than for 1. B is bad for both agents, more for 1 than for 2. And C we're gonna change the value, the common utility for C, and we're gonna look from a case where C is where lambda equals 4, meaning the good C is very valuable to both of them, and then decrease it progressively to make the problem less and less positive until the problem becomes negative and things start being a bit messy. So for instance, you see that for 4 and 3, the problem is positive because, and to check that, you just need to check that you can make everyone happy. So if you for 3, let's say for 3, if you ask agent 1 to eat the bad A, this utility 1, the agent 2 eats the bad B, this utility of 1, and you divide the good 1/3 each, so they each end up with a 1/2 positive utility. So that's okay. So now it's not exactly a movie, but it's if you go fast, it resembles a movie. So this is the case where lambda equals 4, right? Where you see the shaded area, of course, is the set of feasible allocations, and everything works well because we ignore anything except the positive hortant, and we maximize the Nash product. That's the case where lambda, initially lambda was, 4 or 3. But anyway, it's the second case where lambda is 3. And you can still make the two agents happy, but with level 1/2. So things are not as good. And now we get the null problem, the problem with lambda equal 2, when you can barely make them not suffer, but you have no choice, no other choice than that. And now we go to -1. -1. It still looks like a Nash product story, right? We are in fact here minimizing the Nash product as long as we accept the side, because the Nash product, well, what we are minimizing is the Nash product of the absolute values, and forgetting about the fact that it's negative. So it's still appealing, because it's a fair way an unambiguous way to share the burden. But now here is where it starts being more tricky, because, so this is at, I think it's at -2, because now we have 3 points. You see, the same parallelogram same shape for the feasible utility profile. And those critical points, you see that there is one critical point at the peak, at the kink of the feasible utility set, right? So that's okay, because indeed they share a common hyperplane. Then there is 2 other critical points, which are one of them, the curve in the middle, which is tangent inside and then exits the indifference, exits the set, and then a third one over there. Okay, so all right, and then you continue. I think here you are at -3. It becomes a bit hard to see, but and this time you don't have the kink anymore. But you have, it's not exactly pretty, right? And then when you go down even more, things simplify, because now the situation becomes really bad, and you end up. I think this is the level -4 or something, and now you are back to something similar to what you started. So you see, it still resembles very much, and it's certainly deeply connected to the idea of the Nash product, because each time those curves, of course, were the product of the absolute value of the disutilities. So, but it is more complicated. And the other thing that's important is that, you know, this selection problem, here I give an example where you have a certain pattern of utilities, you know, all negative, I mean, to show that the multiplicity can happen independently of the fact that you mix some goods and some bads. I mean, if you, as long as you take bads only, you don't have something symmetric to what happens when you have only goods, because you can have multiplicity. We have some, in the paper, there are some computations of, you know, you can have up to 2 to the power minimum of cardinality of n and cardinality of a of different allocations. So it's really the problem that you know, if you are in a case of a problem which is negative, I mean, of course the positive problems are fine. I mean, but the negative problem can give you a lot of difficulties. Now, look at this. We don't have, as we know, we have multiplicity, but maybe at least we could say, oh, well, maximizing the product of these utilities on the negative frontier, that's fine. I mean, that gives you something because it always appears in there. It selects almost surely a unique allocation. I mean, but as you saw, I mean, there are cases where, of course, the Nash indifference curve can be critical in 2 different points of the feasible set. That's but the difficulty is that at the point where it becomes multiple, the rule that you select jumps. You do not have a continuous selection of your solution, which is a serious problem, because when you have multiplicity and you must choose one of the allocations, you know that a minuscule error can make you change. Minuscule change in the data will make the solution jump very, very much. Yes. Yes? Say that again. Oh, okay. Thank you. All right. So, more impossibility theorems. This is a different paper, but okay. It shows that you know, if you simply concentrate on the bads, not doing too much with the mixture with positive, but just concentrate on the bads and even concentrate on linear utilities, which is always in that theory the good case, you know, where all the resource monotonicity and population monotonicity are satisfied by the competitive solution and so forth. Okay, so you know, as soon as you have 3 agents and at least 2 bads, we cannot combine envy freeness and Pareto optimality in a continuous way. Okay, so not only your set, your multi-valued set of competitive equilibria is discontinuous as a correspondence, right? It's upper hemi-continuous, but not lower hemi-continuous, so it has jumps. But even if you forget about the competitive price and you just say, I'm happy with just envy freeness, which of course is satisfied for the competitive, then you end up with a set of Pareto optimal and efficient allocations with multiple connected components. And same thing, I mean, no possibility to select in there, because this multi-valued correspondence is again upper hemi-continuous, but not lower hemi-continuous, which means that sometimes you know, some components disappear, and then you have 2 components, then all of a sudden you have, sorry, 1 component, then 2 components, then 1 component. When you move a tiny bit, and you cannot select. And no envy, of course, is much less demanding, but that's already enough to give you a good impossibility. Okay, uh, even similar. I mean, no welfare, no single valued rule, which at least in welfare is single valued, which will satisfy the Pareto optimality, the resource monotonicity, and the fair share. So not only these competitive interpretation following no envy has real issues here, but here it's the solidarity approach driven by the axiom of resource monotonicity. Here it's not even that it cannot be used in a continuous fashion, is that it cannot be used at all. I mean, you just cannot respect these monotonicity properties. So I did not prepare an example because they are not particularly useful, but it just gives us a sense that that's really the way with my co-authors we feel for this model with goods and bad or just bads. We are still looking for a different approach. I mean, we don't have much of suggestions to systematically bad. It will not be the right tool. But by what should it be replaced? That's a very difficult question. I mean, it may be that we have to look for subdomains and try to see how to get rid. If we look for subdomains, I think definitely one should look first for the domain of additive utilities, because that's where things are already clearly giving you trouble. And if you cannot propose something meaningful in the case of linear utilities, there is no point, in my opinion, to look much further. Okay, so this is where I stop for today. A little bit early, but again, just before lunch, it doesn't hurt. If you have any questions, don't hesitate now or later. Yes, Joel.
I'm not censoring myself. So
yeah, sure.
There's a story about the three children who were given a will, and they were to divide up the 17 camels of the parents.
Mm-hmm.
And one was to get a half, and the other a third, and another a ninth. And the village wise man comes in with a camel,
Right.
and solves the problem. The
Right.
question is there any notion of a catalyst that you can use to solve these hard problems? That is to say, you have a fair division problem that doesn't fit your criteria, but you bring in something that makes it tractable,
Mm-hmm.
but doesn't use up the resources of the tractable agent.
So maybe, yeah, that's a very good suggestion. I mean, that story of the camel, I'm not repeating it. If you don't know it, we will tell you at lunch, but it's very good. Yeah, you bring a little, it's a little bit like VCG and budget balance. You bring a little extra resources, you then can apply the proper concept and then see, okay, well, can we determine where this extra resource would be minimal? In fact, yeah, I mean, the way you put it, you could ask, if I have a problem where the problem is negative, can I estimate how much of what commodity it would take to make it at least zero, to at least a null problem, and then transform the question to how do I divide these extra resources? That's good point. We never thought of in those terms. I mean, so I don't take that as a criticism. I take that as a very good direction to try to punt. Thank you. Thanks.
I'll leave the room now.
Does someone have another doubt? want to ask
Thank you.
something?
Then thank you, no problem. Yeah.
So now it's lunchtime at the restaurant for the VIPs and the fourth floor here of FEA-5. And then at 1 and 10 p.m., we have two semi-plenaries here in Auditorio 1 with Professor Des Premont, have the semi-plenary Stackelberg's Market Form Stability, and in Auditorium 3, in the library with Professor Neyman, is the Sunk Cost Principle universally valid? So that's it. Good lunch for everyone.
If any international student needs reimbursement, you may follow me, okay?
É o Edu que não achou o outro lá. Você ligou lá pra cima? Não, tudo bem, mas pô, as figuras, né? O cara não entrou aí.
Hello, Claude. Can you hear us?
Oui.
Now I can hear you a little bit. Yeah, I can hear a little bit low. Low. Can you increase the volume a little bit? Okay, we'll start in
Do you
about.
hear me?
Yeah, I
Do you
can.
hear me?
Yeah, I can hear you.
Okay, very good.
Well,
Now I can try to give you the document. Non, je connais le mot.
Reviens sur nous,
Mais comment ça? Partager.
Voilà, partager. Là, qu'est-ce que tu dois faire?
Il a été exclu. Il a été exclu parce que pour moi qui va me rappeler, je suppose.
Je sais pas. Mais je sais pas quoi.
Je ne vais pas mettre quitter.
Ah non, non. On va essayer de
On a dit
partager.
qu'on était dans une waiting ring.
Essayer de partager quand même.
Pour l'instant, je ne sais pas. C'est bon.
Mais non, mais je ne suis plus là.
Non, mais c'est pas grave.
Personne ne voit parce que c'était anciennement.
You wanna try sharing your screen?
I want to what?
Share screen.
Share screen. Okay. Here we are. Partager. No, it doesn't work. I am excluded, it's written.
You're excluded.
I have been excluded.
Alors, je sais pas, peut-être que tu dois recommencer.
Should I start again?
Parce que là, you're stuck on this.
I am stuck on.
Voilà.
Ouais, quitter alors. Hop.
Voilà.
Here I am.
Alors maintenant, on va prendre le truc. Est-ce que tu es en ligne là?
Bon, attends,
Voilà, tu es là.
D'accord.
Vas-y, clique dessus.
OK. Alors, partager, qu'est-ce que c'est? Chat. Ça. Non, non, qu'est-ce que je vais faire là?
Partager.
Voilà, voilà, c'est bon, c'est bon. Clique là-dessus, oui.
Ok, là.
Oh, now I can see it.
Okay, good. Tell me when I can start.
Yeah, in a bit.
Non, bon, c'est bon, non? Je comprends pas.
I am really privileged to introduce Professor Claude Pérez-Castrillo, who will speak on Stackelberg's market form of stability. I only want to add, I met him probably so many years back. His parents, he has some connection with India. Did you study in India for some time? As a
Well, I was a child in India when my father was working in New Delhi.
I see. Okay. So that's the only thing which I have. So I'm so happy to introduce him. Thank you.
Thank you very much. Okay, let me start by saying that it's really a great honor and a great pleasure to participate to this beautiful conference, and also to have online, of course, but to have the possibility to hear many presentations of friends and others by YouTube. So that was very nice, and I thanks also Marilda for inviting me. Thank you very much. So what I will speak about today is at the intersection between the history of economic thought and game theory. And it will be essentially on a forgotten concept presented by Stackelberg, which is market form stability. The traditional view of Stackelberg is quite different because it's focused on the asymmetric leader-follower model. But usually this model is presented by saying that the asymmetry is a time asymmetry, and that the asymmetric equilibrium is a perfect equilibrium of two-stage game. However, in Stackelberg's book, we do not find this specific time asymmetry. He speaks about a behavioral asymmetry with the leader becoming independent and having an aggressive attitude of market dominance, and the follower engage in a dependent or complying attitude. This gives four different market forms: the two asymmetric and the two symmetric market forms. So asymmetric, it's independent, dependent, and symmetric, the same attitude by both, either the two are dependent, have a dependent attitude, or the two have an independent attitude. And so, in fact, there is four possibilities, and so Stackelberg tried to introduce a criterion to select among these four. And his model is applied both to quantity or price games, with the possibility of introducing heterogeneous products. And what he wants is to find what he calls a stable market form, or stable pricing form, because he has the two terms in his book. And here are the two criteria. The two criteria. Well, the first criterion is essentially to say that given the attitudes of the two duopolists, no one should want to change the pricing or the quantity choice. And so it's an equilibrium in price or an equilibrium in quantity. But then he has a second criterion, which is that the behavior of any duopolist should not be willing to change the attitude, to change attitude. And these two conditions apply independently of any time requirement. And this is exactly the market form stability concept that we will be focusing on. But unfortunately, the conclusion of Stackelberg investigation is mostly negative. Instability prevails, or the problems of symmetry. In terms of existence, for Stackelberg, the natural attitude for each duopolist is the independent behavior, aiming at market dominance. But if both duopolists choose this conduct, this leads to what Stackelberg calls the Bolle duopoly, but in fact, he sees that neither condition A nor condition B holds. So that was a very bad conclusion. In terms of symmetry, there are two possible stable asymmetric market forms, but according to Stackelberg, condition B can only be satisfied if the duopoly is itself asymmetric. But unfortunately, in the examples that he looked at, this is not the case. In some sense, Stackelberg was considering that asymmetric market form stability should be an exceptional case, which can only occur if the individual relationship, in particular the cost and production functions of the two duopolists, differ from each other considerably. So what we do, we shall first illustrate this dissatisfaction in the two examples that Stackelberg develops. And very simple example, perfect substitutability and symmetry. And then we enlarge the Stackelberg model, unifying the treatment of the two forms of competition in price and in quantity by introducing a price quantity game. In fact, by doing this, we enlarge considerably the set of possible competitive attitudes to a continuum. And this will allow us to propose a tentative solution to Stackelberg dissatisfaction. So just some reference. Our first attempt in developing this model, this price quantity model, was with Louis-André Gérard Barret and Rodolphe. And unfortunately, Louis-André was dead when the article was published. Then we have another article which introduced some aspect of what I will speak about today. And then recently we have published a small book about the concept, but not about Stackelberg stable market form. But one should say that Stackelberg negative conclusion could explain why this concept of market form stability seems essentially absent from the literature. There is an exception, which is Leontiev review, which has adopted a conjectural variation approach to explain this concept. Of course, there have been other approach to try to endogenize the choice of attitudes. One very well known is to endogenize the timing in duopoly games. So Hamilton and Slutsky consider a three-play stage where the duopolists choose the time of taking actions in the basic game. And also many other authors, Amir and Grillo is one example. But this is not the direction that was privileged by Stackelberg, because it just reinforced the time dimension of the model. Outline, I will first start with the Stackelberg canonical examples. Then I will do this enlarging of the Stackelberg model to a continuum of attitudes, following our work, our preliminary work in other articles. And then we will come back to Stackelberg market form stability and give a new definition of this concept. Stackelberg's canonical examples. In Stackel's view, based on general experience, it can be expected that the independence point is the best point for each producer, and this is valid whenever the demand function is close to being a straight line. This is the privileged example of Stackelberg. This is his first example, which is a homogeneous duopoly with quasi-linear inverse demand. And we will assume nil cost for simplicity, but this can be changed. But in this example, there is a leader advantage. The follower's reaction curve is decreasing, and the second Marshall law is respected. The elasticity of the substitution and the rate of substitution is greater than sigma. So, and in addition, Amir eccentricity holds in this example. So we really have the Galois leader advantage property. Now, assuming that I is a leader, we can, in this example, easily compute the independence point, where Rj is the reaction curve of the firm J. And for Stackelberg, the corresponding asymmetric market form satisfies condition A. If we look at symmetric market form, where both I and G adopt the same behavior, we have two possibilities, either the Cournot equilibrium or the Bowley duopoly. But in fact, as except when everything coincides, condition A is only satisfied for Cournot. To check stability condition B, we can compare the profits of the various market forms, of the four market forms. So pi B is the Bowley solution, and you see that it's equal to 0 here, and it's the worst case. Then you have the highest point is for the leader when there is the asymmetric market form where he's leading, and then we have Cournot, and then we have the follower profit. So the conclusion, if you look at this payment, is that we have two equilibria in competitive attitude, the two asymmetric market form. And for Stackelberg, this is very unsatisfactory, because in some sense, there is a problem. Both leaders would want to be a leader, and then to achieve his position of independence. And this is how we get to the Bowley duopoly, and then it's a catastrophe. Okay. In the second example is the inverse demand is supposed to be this exponential, and it leads to a leader disadvantage. And the follower's reaction curve is increasing. So it's a completely different example. And there, assuming nil cost is important, because if we switch, as Amir has shown, if we switch to positive cost, this property of leader at disadvantage might disappear. Here we get another ranking, another ranking, and you see that it's the follower who has the highest payoff. And again, here there are only two asymmetric. The two equilibria are the two asymmetric market form. But here, the dependent supplier is not tempted to adopt an independent conduct. And the Cournot is not an equilibrium. So, as emphasized by Stackelberg, the main problem remains by permuting the asymmetric conducts, we obtain two potentially stable market forms, but now even worse, each being more profitable for the dependent supplier. Now we switch to our model, which has the purpose of enlarging Stackelberg model. The Stackelberg can be nested in a larger model where firms compete in price quantity pairs, and it allows for a continuum of duopolistic equilibria, including the symmetric and the asymmetric equilibria in price and quantity analyzed by Stackelberg, both for homogeneous and heterogeneous product. And so, for simplicity, we will assume a differentiated duopoly with linear cost and a representative consumer with separable homothetic preferences. With this assumption, there is a price index and a quantity index, a sub-utility, a price index capital P and a quantity index Q, and a demand function and an inverse demand function. And we assume linear cost and possible fixed cost, phi1 and phi2. What is a duopolistic equilibrium? So a duopolistic equilibrium is a pair of price quantity where each firm maximizes its profit under two constraints. There is a primal constraint. So we can formulate the model in two ways, either by using the Hixian and the Marshallian demand. And so we have an Hixian demand, and so QI should be less than or equal to the Hixian demand, and Marshallian demand, capital Q less than or equal to D. So there is a market share constraint and a market size constraint. Or we could take the inverse of these constraints, what we call the dual constraints, and the set of equilibria will be the same, whatever the two constraints. And in addition, we require that these constraints should be saturated at the equilibrium, so that the consumer is not rationed, and that profits net of fixed costs have to be non-negative. So that's the main concept that we will be using to analyze the Stackelberg problem. Of course, we can parameterize the equilibria if we denote the Lagrange multipliers associated to a specific equilibrium. We can do it either in the primal version or in the dual version. And then we define the relative shadow price of the market share constraint by taking the ratio of the two Lagrange multipliers. And this is very important because we are going to interpret this as a measure of toughness of the competitive attitude of firm R. So this is where, the competitive attitude is exactly the idea of Stackelberg. And in fact, we can show that we can recover the four attitude of the attitude that Stackelberg proposed in this model. Now, to parameterize equilibrium, we take the first order condition, either in the primal form or in the dual form. In the primal version, we have the market share of firm I, alpha I. We have the intrasectoral elasticity of substitution of the Xian demand, so S, and sigma, the intersectoral elasticity of substitution. And the first order condition is the relative markup is the harmonic mean of the inverse of the intra and the intersectoral elasticity of substitution. So in the dual version, instead of the harmonic mean, is the arithmetic mean. Now we can look at all the set of potential equilibria by varying the deterministic competitive attitude. In general, we cannot get the whole spectrum of duopolistic equilibria. But we generally get a continuum of the duopolistic equilibria for some admissible set, so some admissible subset. Now, to see some particular case, for instance, when the two Lagrange multipliers are the same for the two constraints, the two constraints can be melted into a single one. And so in the primal version, we then get the price competition. Similarly, for the dual version, we get the quantity competition. So we recover some cases that Stackelberg considered. Now, under linear cause, the claim profit firm can be written as a product of the markup, the market share, and the whole market expenditure. So the homothetic separability and the number of competitors reduced to two allow us to a common intrasectoral elasticity of substitution. So that's why the elasticity of substitution is not indexed by firm I or by firm J. It can be viewed as a function of the relative price. This is also the case for the budget share. So that's a very important property that we will use for our example. To ensure monotonicity of alpha I star and the price ratio, we may assume in addition that the duopolis products are substitutes or complements for any price combination. So they cannot switch from one case to the other. So that we can invert the decreasing or increasing function alpha I and obtain the ratio, the price ratio, as a function of alpha I. And also we can write then the intrasectoral substitution as a function of alpha I. The demand function is assumed to verify the first and second Marshall law. So now if we take these two, the two first order conditions, with this simplifying assumption, the profit function as a function of the attitude of the attitude parameters, theta 1 and theta 2, is well defined. And this is, of course, what we will use very importantly to define stability. Now, if we look now at asymmetric market form, we suppose that firm J competes in quantity, adopt a dependent attitude. That's an example. Compete in quantity, adopt a dependent attitude, and that firm I try to reach its independence point. And suppose that it exists. This the problem is that this independence point may or may not be enforceable as a geopolitical equilibrium. Because here, and this is different from Stackelberg, we have more deviation because the leader is not restricted by the reaction function of his rival. If it is enforceable, so it may be not enforceable, but if it is enforceable, then the market form where the follower adopt a dependent attitude is such that the attitude adopted by the leader maximize his profit over the corresponding admissible set. So the leader anticipates his rival's attitude. So in some sense, this gives a new definition of what is an independent behavior. The leader tries to maximize his profit considering the attitude of his rivals. So if we compare that to the sequential model, the first mover advantage or disadvantage in the two-stage game translates into a more aggressive attitude of the leader in the simultaneous game. Now let's come to the market form stability definition in this new model. So limiting market form to the admissibility set ensures that condition A holds. To further ensure that condition B holds, we suggest the following definition. Let omega H be admissible market form. A market form is Stackelberg stable if it is an equilibrium in the parameters theta. But it's an equilibrium where the choice of I are limited to a pair which satisfy condition A, which are equilibria. Now let's come back with this new definition to the two examples. In example one, we have a leader advantage. The independence point is enforceable as a duopolistic equilibrium. But now the two asymmetric market forms are not as stable. Existence of a continuum of competitive attitude makes now a deviation admissible in our framework. So condition B is reinforced. In that sense, we go in the direction that Stackelberg wanted, in the sense that we eliminate the possibility of these two asymmetric market forms. On the other hand, a symmetric S-stable market form can be derived from first-order condition and can be viewed as a revisited Borley market form, because now this revisited Borley market form will satisfy both condition A and condition B. So in that sense, this new definition is much more satisfactory from the point of view of Stackelberg. In example 2, with leader disadvantage, the independence point of each duopolist is unenforceable as a duopolistic equilibrium. And the Cournot equilibrium price is the highest enforceable price. There, the Cournot market form is less stable. Remember, in the Stackelberg approach, this was not the case, because a deviation leading to a price higher than the Cournot price would not lead to a duopolistic equilibrium. In both examples, as switched by Stackelberg, the two asymmetric market forms, identical up to a permutation of the duopolist, are not as stable. More generally, we have proved some more little more general result, but let me skip that. So we can go outside if we have enough symmetry, we can go into the differentiated good case. There is not homogeneity is not always required. Now the example, if we come back to example one, remember in example one we had in example one we had assumed that the costs were nil. Now, when we change in example one and assume that the costs are positive and the fixed costs also are positive, the marginal costs are positive and the fixed costs are positive, it's much more difficult to find a stable market form. And so one possibility is to see, because in some sense the concept of stability require that the equilibrium should be a social equilibrium in the sense of Debreu, because you have the admissibility constraint is limit the choice of strategy by the duopolist. Now, if we take in this example the first order conditions, we get two markup equations that can be solved for the price P and the market share ratio. And they appear to be function of the product theta 1, theta 2. An stable market form is a double social equilibrium in competitive attitudes. So what we to ensure existence, we can look at Debreu's theorem and see if the condition of Debreu's theorem are satisfied. So in this example, the admissible price range is between two price, the price PC, the Cournot price, which is the highest price, highest possible price, and then P bar, the lowest, is the floor below which one firm cannot cover its fixed costs. So we certainly have to be in this price range. And this translates into an admissibility condition on the competitive attitudes, those allowing the competitors to remain active at the Cournot price. So we have theta I should belong to 1 to the interval 1 theta bar I. So we may take the interval as the set of a priori available action for duopolist J. And we can check that it is non-empty, compact, and convex. First condition. Second, much more difficult to prove, the profit function of firm I is continuous and quasi-concave, and in addition satisfies this condition, means it cuts the horizontal axis at some point theta tilde J, and this finally we shall use this condition to check the third condition, the third assumption needed, which is since the profits must remain non-negative, admissibility is finally given by the convex and continuous correspondence omega I theta G, which use this definition, and so the Debreu's theorem applies. Now, of course, this is just an example, but it shows how this theorem, the Debreu's theorem, can be used in this context to find stable market form. Conclusion, our aim was to revisit a forgotten concept introduced by Stackelberg, market form stability. We have tried to alleviate Stackelberg dissatisfaction, and we have succeeded at least in the two main examples that he has developed. And we propose a more formal definition of market form stability. And this definition, in fact, strengthens both condition A and condition B. But the interest is that we address some of the Stackelberg concerns. Of course, all this can be generalized. First of all, in terms of, we can certainly switch from duopoly to oligopoly. That's because all the model we have developed before were oligopolistic models, so that will not be a problem. The concept of stability can certainly be also generalized. That's certainly true. Of course, more difficult is to go beyond the simplifying assumptions that we have introduced. In our previous work, we have other type of assumptions that work also, but we have to investigate that. And of course, to prove existence of a stable market form is in these generalization is to needs much further work. Thank you very much. I don't know if there are some questions.
Thank you very much, Professor Rasmussen. Do you want to come here, Professor Raghavan?
Any questions? We have time for that. We have to chew. It takes time. I understand. Thanks a lot. Nice. Thank you. Thank you.
Thank you very much. Thank you.
So, to 10 minutes, we will have a coffee break until 2:20 p.m. And then at 2:25 p.m. here at Auditorio 1, we are gonna have the invited session number 5 with Professor Bugarin and Wilfredo Maldonado. The topic is sequential auctions, aggregative games, and in Auditorium 2, invited session number 6 with Professor Sandrone, Álvaro Sandrone, and Brian Powers. The topic is principal agent, arbitration, and now is done the certificates of all of you of here, the event IWGTEA, and you can take it here in the secretary until Sunday, all right? So they are done, and soon, 2 p.m., there is the coffee break, all right? That's it.
Good afternoon, everyone. Shall we start? So we are here for this invited lecture. I am Mauricio Bugarin. After me, Professor Wilfredo Maldonado is going to present. We organize so that we present and then we try to leave a few minutes so you could ask questions. But if you feel like making comments while we are presenting, you are welcome. This first paper is co-authored precisely by Professor Wilfredo Maldonado from USP and Professor Odilon Câmara from the University of South California. And this is the outline. I'll try to motivate the paper and then present three simple analysis that we got from it, then conclude. So what's the motivation? Well, many markets, I come from Brasília, a public city, and I'm very much concerned about public procurement, but many markets have these characteristics of being recurring, which means the same buyers, or in case of procurement, the same, the government buys from the same sellers again and again. For example, office supplies from public institutions or private institutions, medicine for public hospitals, they're purchased again, and typically with auctions. So on the other hand, many real-world contracts have this feature of giving an advantage for those who already won sometime in the past. For example, in real estate, the tenants hold statutory rights of first refusal. In corporate agreements, often minority shareholders have preemptive rights to purchase additional shares before outsiders. In intellectual property contracts, licensees may negotiate clauses granting them renewal or expansion rights before the asset is offered to others. So there is this idea of using a little bit, just a bit of past history in the next realization of a recurring relationship. The question we would like to discuss here is, given that many auctions have this recurring property, can the seller use this history in a specific way, giving an advantage to the winner of the previous auction to improve on his expected revenue compared to Meyerson's typical one-shot game? That's the question we'd like to ask. And if so, how can we do it in a simple way, but still improving on the revenue of the seller? So that's what we'd like to discuss here today. So we call this idea of giving an advantage, we call that creating endogenous asymmetry. It's an asymmetry that the mechanism design creates. The participants may be exactly the same ex ante, but due to that mechanism, they will become different, right? And there is a literature on asymmetries in auctions, but a lot is about exogenous asymmetry. For example, the types may belong to different distributions. Professor Meyerson's paper does that. It's very general in that point of view. It may be that they have different information. So participants are different because they have different information. This literature that I call exogenous asymmetric literature typically find that there tends to be, these asymmetries tend to be hurtful for the seller. The seller doesn't do that well because of that. There are asymmetries arising endogenously. For example, suppose I won a procurement and then because of that, I'm able to make investments that reduces the cost. Then in the next procurement that I participate, I may have a technological advantage because I was able to invest, right? There may be cost synergies. If I want two procurements, then I can reduce the unit price because I have more, I'm dealing with several projects and there are cost synergies. In this case, asymmetries are in a certain way endogenous, like mine, but they do not arise from the behavior of the seller wanting to maximize his revenue, rather from some technological characteristic of the situation. And there's also a literature that's close to what we do here that gives special treatment to some buyers. For example, this paper discuss ex ante agreements that grant a bidder right of first refusal, and the result it finds there is that this creates inefficiencies. The paper below there discusses how negotiation between the seller and one of the buyers may improve on their joint return, which is a little bit different from what we want, right? We want to improve the seller's return. So our idea is to create a symmetry among buyers in a dynamic setting so that this could make the participants work harder to win today, and that could benefit the seller. So that's the idea behind it. The result that we find is that this advantage increases competition. Of course, now winning today is not just the good, but the benefit of tomorrow. This increases competition among all participants today, and also it may reduce a little bit of competition later on, because if I won today, I have this advantage, so that will reduce a little bit the competition in the future. But what we prove here is that the increased competition today compensates even for the future reduction of competition, and still makes the seller better off. Our comparison is always Meyerson 1981's model. We are going to discuss that. That's several. No, but we are going to actually design the auction, and we are going to study one specific one, that's the price matching mechanism. But then we are going to discuss in a more general way, and you'll see in a minute. Just to give you the flavor, look at 2 auctions, just 2. And there are a certain number of players, 2 objects. At each period, the values are private, independent, across periods and across participants. And we know well how these auctions work, but we add this price matching opportunity. So how does it work? If someone wins the first auction, then the next auction, that person can match the highest bid or the price of the auction. So it depends on if it's first price, second price, etc. The benchmark we know very well, thanks to Professor Meyerson. We consider two situations: when a reserve price is not applied, and then when the optimal reserve price is applied. In both cases, when we use this price matching opportunity, there is a gain in the expected payoff of the seller. Here, you know, first price, second price doesn't really matter. And when we do use the optimal reserve price, there is still a benefit of working this way, of offering this opportunity. It's a little bit smaller, but there is still always beneficial to the seller. Now, one interesting thing is that, you know, the optimal reserve price is a very good theoretical result. May not be that easy to implement or to choose correctly the reserve price. When we compare this price matching mechanism with without reserve price, with the mechanism with optimal theoretical reserve price, it's still better, except for 3 players. If there are more than 3 players, it's still better. So it helps also to solve this issue of how do I get in practice the optimal reserve price, right? But that's just to give us a flavor of the result. This is very simple. It works for uniform distributions, and now the question that comes is, does it work for infinitely repeated games? And here we first start with one specific model, the same price matching, that allows the winner of today the possibility of matching the equilibrium price of tomorrow, of the price of tomorrow. So the setup is pretty basic. N player, the risk neutral players, one seller, infinitely repeated game. The seller has no value for the good, independent private values across bidders and periods, regular distribution with full support, and what matters then is whether the object was sold in the past. For example, in the first period, it's not sold, so it's 0. And if it's sold, what is the identity of the one who won? That's all that matters in this model. And then the game starts. In state I, the one who won previously becomes the incumbent, we could call like that. And we know, thanks to Professor Meyerson, there is an optimal reserve price. It may be binding or non-binding if the V lower bar is positive. If it's binding, we know where to find it. If it's not, the lowest price. And then we can work this equilibrium. We need to compare the revenue of Professor Meyerson's setup, here RI, and then what would be the expected revenue in the entire history with this new model. So we normalize to be able to compare in a per period model, in a per period comparison, and we call that R0 price matching. Delta is the discount factor. And what we were able to prove is we're able to find an identity that relates to the order statistics, the difference in the first and second order statistics, that relates the benchmark model to the price matching model. That shows that the price matching model gives a higher expected payoff for every discount factor. And this result that we first proved for the case where the reserve price is not binding, we can extend it to the case where reserve price is also binding. So for this specific rule, that is, you can match the price of the equilibrium price. This works better for the seller than the standard, just repeating the optimal auction. Now, this is a very specific one, right? We could ask ourselves, can we have a more general result? Just asking for following the same idea of giving an advantage, but the advantage may be different, maybe something else than price matching. We know price matching works well in terms of giving a better result, but can we say what's the best auction? With this restriction, we want the price, we want the winner to get an advantage, and we want to do it in order to maximize the seller's payoff. So that's what we do here. We set as a goal to maximize each period's revenue, expected revenue. We define what's going to be the mechanism that's going to be applied every period. And the rest is the same as we discussed before. And the point is that the winner receives an advantage. We don't know exactly what it is, but it will allow the winner to get higher payoff compared to the other ones. That's the idea. So how do we design the auction this way? It's a very simple differentiation from the basic model. The winner gets an advantage, the other ones are treated symmetrically. They're just the same. They just don't get that advantage. Then, by the revelation principle, we focus on direct revelation mechanisms. the state variables is the identity of the previous winner. That could be 0 if either it's not solved or it's the first period. And then we can work, well, we are looking for a mechanism that defines the probability of the good going to bidder I, given the state, given what happened, very specifically who was the winner last time, and how much he is expected to pay using the traditional technology that we got from Professor Meyerson. And we want to solve this problem to maximize each period expected revenue. And then we know what is the benchmark from Professor Meyerson's work. We have this virtual value, and depending on the maximum virtual value, we choose the one who will receive the good and the price and everything. In our case, we need to be a bit more careful because at each period, the participants think about what happened next. So we define U upper L, the expected utility of a winner after in the next periods, and W of a loser. And this difference is what makes winning today more attractive compared to the basic model. And this reflects the willingness to pay of an agent. And then we do the math that Professor Meyerson told us how to do. And we get an intermediate result that shows that not only that part that looks very much like the basic model, but this additional part that says by giving an advantage to the winner, the seller gets some money out of it too. So that's the idea, right? So we work some more, and then we get this is what we find a very interesting result. So what were the virtual values now splits into two types of virtual values. One is the virtual value of the winner that is increased, you can see, compared to the other one, compared to the benchmark. And the other one is the adjusted virtual value of the losers, which are decreased. So what we find when we solve in the very, very traditional way that Professor Meyerson told us how to do is this inequality here. So compared to the standard model, the winners are less valued in a certain way by the mechanism. The losers are less valued. The winner is more valued. So the winner gets two advantages. It gets lower reserve price and lower payment. So this is the main insight of what we found about this optimal mechanism. We can analyze what happens in terms of comparative statics. The number of players doesn't affect the adjusted virtual value of the winner, but it does affect the virtual value of the loser, because the more players there are, the less significant it is, disadvantage, right? Because all values, higher values are more probable. So especially when n is small, then disadvantage is very important. As it increases, it's not that important. And regarding the discount factor, this is, as we would expect, as players become more patient, the future is more valued. If the future is more valued, then this advantage is higher. So you can see here delta higher delta, still higher adjusted value for the winner, and still lower adjusted value for the loser. So more patient increases disadvantage and increases the benefit of the winner, but also of the seller. And then the transfers gives a double advantage to the winning, to last auctions winner. So that's what we wanted to do, offer mechanisms that are simple and that have a relationship to what we observe in practice in many situations where a winner receives an advantage. We were able to characterize the optimal advantage mechanism for sale. We just discussed that. Note that this is not an efficient mechanism, because the virtual values are adjusted. It may be the case that the object is worth less for me and I still win it in the next auction because I have this advantage of having won the next one. Also notice that our goal is not to fully characterize among all possible dynamic mechanisms which one uses the past history and gives the optimal return to the seller. That's not it. What we wanted to say, there is a little small modification that we can do that is intuitive, that we can actually sell to the authorities or to the mechanism designers, that improves upon the basic model, improves up the expected revenue of the seller. So that's it. Thank you very much. Now,
Doubts, guys?
You could ask questions, or you can go.
Or can we afraid to start?
Professor Maldonado. You can also ask questions when we are finished, right?
Good afternoon. I want to thank Marilda Sotomayor for inviting me to share with you some ideas regarding some papers I was working on these latter years with some students, some colleagues. And rather than one paper, I would like to share with you 3 papers and one idea, which is the idea of E-stability in aggregative games. Well, simply, aggregative games is a game with the following characteristics. We have n players, and maybe I can use this. Yeah. We have n players. Each player has a set of strategies, as always, but this set of strategies is an interval of the real numbers. We can define the sum of the possible strategies, and the utility or payoff of one player is depending on the only strategy and the sum of all strategies of all players. The classic illustration undergraduate example is the group of oligopolistic competition, where the strategy is the production of the end firm. We have each firm has a cost, and we have the price defining the inverse market demand, and the payoff function for the firm is this. So we can observe that it depends on the own strategy and the sum of all strategies. A lot of examples we have for these aggregative gains. For example, contribution for a public good provision, the tragedy of commons, pandemic environments, and many more. Usually for analyzing the equilibrium of a game, we use the best response function, best reply function. But for aggregative games, it's usual to use to take advantage of this replacement function. What is the replacement function? First of all, we can define the compensation function, which is this phi, that given the all contribution, the aggregative contribution, and an amount that it is diminished from the total contribution. So the compensation function is what is the individual contribution that compensates this diminishing of this aggregative contribution X. When this contribution equals this Y part, we have the replacement correspondence. This replacement correspondence can be seen as the optimal contribution in the composition of the total amount of the aggregative gain, the aggregative contribution. And if we have a Nash equilibrium for the aggregative gain, then each element of this profile is equal to the replacement function applied in X star, where X star, capital X star, is the sum of all contributions. With these replacement functions, we can define the perceived to actual map rho that is defined by this expression. Rho of X is equal to the aggregation of all replacement functions applied to X. We can interpret this as the actual contribution given a perception of individual perception that X is the total contribution in the game. And it's simple to use this perceived to actual map to find the Nash equilibrium. The Nash equilibrium is nothing else that a fixed point of this perceived to actual map. So the analysis of the equilibrium become only one-dimensional analysis. The literature on aggregative game is very huge. So we have a lot of contribution, starting with Selden, with a pioneer work on aggregative games, following what Novchek, using this in 1985, the existence of equilibrium applied to Cournot games. Afterwards, Corchon makes comparative statics. Jensen connects the aggregative game to potential games and best reply dynamics. Jensen, in a section of a handbook of game theory in industrial organization, has a comprehensive and rigorous presentation of aggregative games. Cornes and Hartley defined the replacement function for fully aggregative games and simplifies the analysis of existence of equilibrium. Well, let me start with 3 applications of these aggregative games that we recently worked with some co-authors. Agricultural fires. We suppose that there exist N farmers. Each one has owned a piece of land. Tn is the piece of land of owner N. The total land dimension is T, which is the sum of all parts of the land. And this is the strategy that each farmer will decide. The part of the land that he decides to prepare for agriculture using fire. So D is the sum of the total burned area used to prepare using to prepare the land for production. The production of the farmer is the classical one, the Cobb-Douglas production function, but we introduce here shock that the productivity of the land will decrease with the total burned area in the region. So this total burned area may diminish the productivity of land, causes damages to the nature and anything else. This A function is a decreasing function and concave function. C is the cost of the agricultural fires that we can interpret like an expected fine that the farmer will receive for burning. So the aggregate gain is defined by this, the payoffs for this aggregative gain is defined by this way. This is the production, sorry?
Positive. You've written negative, but
it's negative because the more you burn the total area, it's more difficult to produce.
So productivity goes down if you burn more.
Yes, productivity goes down.
Thank you.
Mm-hmm. Thank you for that. And this is the payoff function. This is the total production minus the total cost for burning. Equilibrium exists with this simple hypothesis. And unfortunately, not always it is interior. We have in the paper some hypotheses on the productivity of land that give us the result of interior equilibrium. And if the equilibrium is interior, then it is unique. It is necessary to perform a comparative statics analysis. So if the equilibrium is strictly positive, so it is interior, all the fines are the same for all the farmers, and these other technical hypotheses, then the total amount of deforestation depends increasingly in N, more farmer, more deforestation, and decreasing in the fine. Higher fines diminish the deforestation. So we have a relationship, an inverse relationship between N and K that preserve the unchanged. We have a relationship between the amount of fines and the number of farmers that keep on changing the star. And this is the other interesting result that we have in this paper is if the equilibrium is positive and the fines are the same for all farmers and this technical hypothesis, the total production of the land, of the region, has a U-inverted shape regarding the fine. So small fines has a small production, large fines has small productions, so making a simulation with this functional expression for A function for the productivity of land. With these numbers, we obtained, for example, this shape for the total production of the region. So this is a very interesting result that can be used to define what is the optimal fine that can be put for land fires. Other example, other application is another paper that I have with a student, which is in Northwestern, in fact, Freitas with me in social choice and welfare. This quadratic funding is a way to a way to provide a public good. Let me explain how it is. Suppose that we have n contributors for a public good with this classical utility function, quasi-linear utility function, with this utility has the usual hypothesis, increasing and concave. A funding mechanism for a public good is simply a function that for each profile of contributions makes a total amount of the public good that it's provided. Usually, this phi function is the sum of C1, C2, and Cn, but not necessarily is equal to this sum. The public welfare agent may select another function phi to provide this public good. A public good provision game is defined by this expression, by this set, utilities, and a definition of a funding mechanism. And as always, an equilibrium, C star, is a profile that deviating from this equilibrium leaves the agent worse off. And the efficient provision of the public good is simply the one that maximizes the total welfare of the economy. So the idea is when I can find that this efficient contribution can be reached from an equilibrium for some funding mechanism. So we have this extension of proposition given by Bugarin et al. In management science, which we revisited. And if using this hypothesis of monotonicity and concavity, and using this funding mechanism, which is a CES function, if C star is a profile that is an equilibrium and FE is the efficient allocation, then we have these three situations. If rho is between 1 and 1.5, we have under contribution for the public good. If rho is lower than 1, we have over contributions for the public good. But if rho is equal exactly to 1.5, then the funding mechanism recovers efficiency in the economy. Thus, the quadratic funding mechanism provides efficient equilibrium, and it is already used for funding software development and charity in United States. Bugarin makes some money with this kind of mechanism. I don't know how much. The quadratic, but what is interesting is that Bugarin comments in his paper that the same must be true in an environment with incomplete information. So my colleague, my co-author, asked if it is true. In fact, if with incomplete information, again, quadratic funding is efficient. And we analyzed this quadratic funding under incomplete information. Under incomplete information is the same, the utility has the same phase, but with types. Each agent has a type. This type may be maybe one of the elements of this theta I set. We have a distribution, probability distribution of the types. And the provision and the public good provision game with incomplete information is defined in this way. An equilibrium, as always, is the version of Bayesian and Nash equilibrium. which is this one. And an efficient provision in this setting is like this. FA for each profile of types is the R masks of the total welfare of the economy. And this is the main result. The main result is that with the classical hypothesis for the utilities, if the efficient provision of the equilibrium is strictly greater than 0 for all theta or profile, and if we have only one individual with more than one type and the other ones has only one type, so we only change it, the possibility, we only assume the possibility that one agent has more than one type and the other ones have only one type, then the quadratic funding mechanism is efficient if and only if the sum of marginal utilities is equal to this inverse of the square root of the efficient provision. So this is a very restricted condition to obtain that the efficiency of the quadratic funding mechanism. This is very similar to a utility which is a constant elasticity utility. So we restrict our analysis now for the constant utility for constant utility functions of all individuals, and we ask when this constant, this CRRA utility is makes the quadratic funding mechanism efficient. And we obtain this, unfortunately, result. The proposition is that if we have individuals with different types, different utilities in two types, then quadratic funding mechanism is efficient all if and only if the coefficient, relative risk aversion coefficient is equal to 1.5. So if the relative risk aversion coefficient is different than 1.5, then we have inefficiency, and we can measure this inefficiency. We define an index for this inefficiency. First of all, we define what is the ex-ante efficient provision. Is something like the efficient provision, but only with the expected value. The social welfare, as we know, is the sum of utility minus the total amount of the public good. And we define this index, the relative deadweight lost for the economy. Is the difference between the efficiency, the welfare of the efficient allocation minus the welfare of the equilibrium allocation divided by this other measure. So we will measure this index for this example, this numerical example. We only took two individuals with this probability, equal probabilities for the types of them. And I mean, n individuals, but each individual has two types, only two types. And those types are equally probable. And the utilities are these, and we can compute the efficient allocation and the ex-ante efficient allocation, and using computational methods, we can find this equilibrium and compute this index, relative deadweight loss. So the efficient allocation is this, the ex-ante efficient allocation is this one, and we have this asymptotic behavior for the relative deadweight loss. Observe this, that if we have the risk aversion coefficient very close to 1/2, independently of the number of the individuals, the number of contributors, is very small, the relative risk aversion, this index, deadweight lost, relative deadweight lost. But if the relative risk aversion is 1/4, 1 or 3/4, we have that as the number of individuals increases, the amount of inefficiency increases. So we are working now with this conjecture that this index of dead weight loss, relative dead weight loss for this model converges to this expression. Well, the last application is the aggregative games applied to pandemic environments, very recent problem. And workers decide how much labor supply, XN, in a pandemic environment. If they are infected, they have to stay at home and they will receive this amount of wage. And if they are not infected, they receive the wage in total. This lambda n may be interpreted as a parameter for policy compensations. And if the total labor supply is X, then the probability of infections depends on X by this function pi of X. So the individual problem is to maximize this utility, the utility of being infected plus the utility of not being infected. As we can see, this is all again, an aggregative game. An aggregative game is defined in this way. So we illustrate this, our model for this utility function and this probability of infections. Lambda n, as I told you before, represents the subsidy policies, and C represents the containment policies. Observe that if C decreases, the probability of contagion diminishes. So the lower is C, the more restrictive is the policy for avoiding containments. Using these parameter sets, this is for guarantee that the utility function is concave, we obtain the following result. With these parameters, satisfying these inequalities, we have this equilibrium for the total amount of labor supply. Observe that if C decreases, the total amount increases. If the number of workers increases, the total amount supply diminishes. And well, we can make a lot of comparative statistics here. Some consequences is if there is more containment, then the total supply labor increases. If we have more economic compensations, the total labor supply increases. What is interesting is that pi doesn't depend on C. It means if lambda increases, then the probability of contagion increases, but not with respect to C. But the most interesting, and is the final part of my presentation, is that this in this framework, there exists a neighborhood of the parameter where we can find two cycles for the dynamics of expectations. What is dynamics of expectations? E stability is the stability with respect to the dynamics of expectation or inductive learning dynamics given by this expression. Given that the people, that the agents of the system perceive it, that this is the amount, the total amount of the contributions, they respond with the replacement function. This perceived to actual map reports the actual amount of the aggregative contribution. So the inductive learning is defined, it was used already by these other researchers. Guénéry presents a notion of as a foundation of rational expectation hypothesis. Evans, Honcapoya, Evans, Guénéry used this Inductive learning dynamics in macro models. Balasco uses this in general equilibrium models. Evans and Guénéry in non-cooperative games. So we are using here in aggregative game, and we will define that X star is expectationally stable if it is stable for the dynamics of expectations in X star. So easily we can define we can realize what when X star is expectationally stable, when the modulus of the rho prime in X star is lower than 1. For example, in public goods, we can analyze this simply. In a public good with n contributors and this utility function, this is not a quasi-linear function. This is a CES aggregation between the amount of money after giving the contribution and the total amount of the public good. This is used in the literature to assess the wealth effect in the public good contributions. M is the initial wealth, X is in the individual contribution, capital X is the total contribution, alpha and beta are parameters. So if we compute the replacement function is this decreasing function, linear decreasing function. It's very simple. As I told you, in aggregative games, it's more convenient to use the replacement function than the best replace function because of the form of the payoff functions. So if each replacement function is linear, the sum of this replacement function is piecewise linear and decreasing. And if all these parameters case defined by this are very close or equal, we will have this perceived to actual map. This perceived to actual map will be this linear decreasing function if X is lower than this parameter and 0 otherwise. So the unique Nash equilibrium is the fixed point of this function. And this Nash equilibrium is expectationally stable if only if the derivative of this is lower than 1. So if n is lower than k minus 1. This is the perceived to actual map. This is the diagonal of the first quadrant. And for example, this is the Nash equilibrium. And if we have this first perception of the total contribution for the public good, this X2 will be the actual contribution. And if X2 is the perceived contribution, X3 will be the actual contribution, and so on. So we can observe that we have that this X star, in this case, is locally unstable. But we have a cycle dynamics around it. So if the slope of this segment is equal to -1, we have exactly a 2 cycle. If n is equal to k minus 1, there exists infinite 2 cycles. Bach and Roy already found these kind of cycles in charity contributions. Cycle in pandemics environment, and with this I will finish. In our model of pandemic environments, we can show that the derivative of the perceived to actual map is equal to this expression with these parameters. And we have the following result. If sigma is lower than this expression, so then X star is expectational stable. So for example, if n is large and gamma is not close to 1, it's very likely that this inequality holds. So X star is expectationally stable. But if gamma is close to 1, so we can have this inequality being held, and X star will be expectationally unstable. what is interesting is if the parameters are exactly equal to this expression, sigma is equal to 2 plus gamma minus 1n, then there exists a neighborhood of this parameter generated 2 period cycles around x star. We use the period doubling bifurcation theorem to prove this. So here are some comments. If gamma is close to 1, may trigger instability of the Nash equilibrium, and 2 period cycle may be attracting or repelling. So if we perturb this equality and obtain sigma greater than this, we will have expectationally unstable, and if it is lower, expectationally stable. And we make some numerical examples with n equal 5 and these parameter values, and we obtain this perceivable to actual map. And this is the Nash equilibrium, and we have an attractive cycle here. If we start with this x0, we will have this x1, this x2, and so on, attracting to this cycle, x1, x2. This x1, x2, in this case, this numerical case is this, and we obtain the probability of contagion being these two numbers. These are the persistent of probability of contagion that we saw in pandemic episodes, where the probability increases and decreases persistently. And we have also the situation of repelling two cycles with other parameters. This was the perceived to actual map. We have here the Nash equilibrium. This is the cycle, and this is the repelling cycle. So again, we have behavior around this Nash equilibrium converging to the Nash equilibrium, and the cycle has these probabilities. So to take away 3 messages, aggregative games is a simple but useful framework for modeling competition and cooperation when payoffs are based on aggregated strategies. Rather than the best response function, the replacement function offers an accessible way to find and analyze the Nash equilibrium. And finally, as an inductive learning process, expectation dynamics can explain cycles and act as a selection criterion for the Nash equilibrium. Obrigado.
Is anyone in doubt, guys?
Any
Does
question?
someone have something to ask to Professor Maldonado or Professor Bugarin? So now we have a quick break, 15 minutes break, and then we can go to the regular sessions in corridor A until the end of the day.
Okay. Thank you. Aquele capítulo do handbook Game Theory and Industrial Organization. Uma avalanche de questões e artigos. Foi essa a minha Bíblia quando eu fui é uma forma você tirar foto. A gente não joga jogando coisas sempre acima abaixo, sempre acima abaixo. E aí as questões podem ficar de maneira
Mas ainda eu ver, porque a dinâmica, uma os caras revisam isso imediatamente. Aí eu tentei fazer algumas coisas, mas isso é uma coisa. E outra coisa. Sempre há. E aplicação, independente do outro, mas eu nem informação para ideia, para ideia. Eu acho que a pergunta mais não sei o que conta. Para que agora depois uma concorrência está uma para baixo, o equilíbrio é estacionalmente estável. Mas a partir do para não é estacionalmente estável. Os caras se afastam e não chegam. Então, aí o cara, o que acaba fazendo? Ele é como se fosse o eu consegui. O problema é que quando você quer fazer isso para outro tipo de jogo, concorrência vertical, aí já o negócio não funciona. Então, possivelmente, tem a questão do desempenho contínuo no lugar do mas não consigo fazer a contínua. Participação direta, também, exato. Vai, não vai. Vai, não vai. Vai. Então, até que eventualmente atrasou, o ciclo atrasou, o ciclo atrasou e converte ao equilíbrio. Para você está falando da responsabilidade que você está fazendo. Mas Mas o problema é que todo jogo é muito. Por isso que eu preferia